What if I told you there's an invisible force right now pushing the entire universe apart faster and faster, yet we can't see it, touch it, or even fully explain it? This isn't science fiction. It's the reality of dark energy, the most baffling mystery in modern cosmology. Think about that for a second. 68% of everything in existence is made of something we don't understand. That's like trying to read a book where most of the pages are blank, and the few words we can see hint at a story far stranger than we ever imagined. For decades, scientists have been piecing together clues about this enigmatic force, and what they've discovered is nothing short of mind-bending. Dark energy isn't just some minor player in the cosmos. It's the dominant force shaping the fate of everything. It's why galaxies are racing away from each other at ever-increasing speeds, why the universe isn't just expanding but accelerating. And here's the wild part. Every time we think we're close to cracking the code, dark energy throws another curveball, defying the laws of physics as we know them. That's exactly what makes this journey so thrilling. Today, we're diving into 42 pioneering investigations that are pushing the boundaries of human knowledge, from Earth-bound telescopes to space observatories peering into the deepest reaches of time. These studies aren't just about numbers and equations, they're about rewriting the very story of our universe. What if dark energy holds the key to understanding the ultimate destiny of everything? What if it's linked to dimensions we can't yet perceive, or forces beyond our current comprehension? Strap in, because we're about to explore how science is tackling these cosmic riddles, one groundbreaking discovery at a time. Let's rewind to 1998, when two teams of astronomers made a discovery so shocking it shattered everything we thought we knew about the universe. The Supernova Cosmology project, along with a competing team, was studying distant stellar explosions called Type 1, a supernova, cosmic beacons so consistent in brightness they're nicknamed standard candles. By measuring how dim these supernova appeared across vast distances, scientists could calculate how fast the universe was expanding over time, but what they found defied all expectations. Instead of the slow, graceful deceleration predicted by Einstein's equations, the data revealed something astonishing. The universe wasn't just expanding, it was speeding up. Imagine throwing a ball into the air, only to watch it blast off faster into the sky instead of falling back down. That's the equivalent of what these observations showed. The dimmer-than-expected supernova meant space itself was stretching at an accelerating rate, as if some invisible force were pressing harder on the cosmic gas pedal. This wasn't just a minor tweak to the rules, it was a revolution. For decades, scientists had assumed gravity would eventually slow the universe's expansion, maybe even reverse it in a big crunch. But dark energy flipped that script entirely. The team's findings were so monumental they earned the Nobel Prize in Physics in 2011, cementing dark energy as the dominant force in cosmology. Yet for all its significance, the discovery raised far more questions than answers. What could possibly be strong enough to overpower gravity across the entire cosmos? Why hadn't Einstein's theories predicted this? And most haunting of all, if the acceleration continues, what does that mean for the ultimate fate of everything? What made this revelation even more extraordinary was how it connected to Einstein's oldest mistake. Decades earlier, he'd proposed a cosmological constant, a mathematical fudge factor to keep the universe static. He later called it his greatest blunder when Hubble proved the universe was expanding. But now, suddenly, that same constant might hold the key to dark energy. It's as if the universe had been hiding the answer in plain sight all along, waiting for us to catch up. To truly grasp the profound influence of dark energy, we have to look back, way back, to the universe's very first light. Picture this: 380,000 years after the Big Bang, the cosmos had cooled enough for atoms to form, releasing a burst of radiation that still lingers today as the cosmic microwave background, or CMB. Think of it as the universe's baby picture, a snapshot frozen in time and etched into every direction of the sky. But here's where it gets fascinating. The Planck satellite, Europe's most advanced space observatory, spent years mapping this ancient glow with unprecedented precision, revealing subtle temperature variations, tiny ripples no larger than 1 part in 100,000. These aren't just random fluctuations, they're cosmic fingerprints imprinted by the push and pull of dark energy in the universe's infancy. What makes these patterns so revealing? Imagine tossing pebbles into a pond. The ripples they create depend on the water's depth and texture. In the same way, the CMB's ripples reflect the universe's underlying structure, how matter clumped together, how space expanded, and crucially, how dark energy began shaping everything. Planck's data showed something unexpected. The distribution of these hot and cold spots didn't quite match predictions based on gravity alone. It was as if an invisible hand had subtly tweaked the fabric of space, smoothing out some regions while stretching others. This anomaly points to dark energy's early role, challenging the long-held assumption that it only became significant billions of years later. But the real breakthrough came when scientists combined Planck's CMB maps with other cosmic measurements like galaxy surveys. The mismatch was undeniable. The universe's expansion rate today, measured by supernova, didn't align perfectly with the rate inferred from the ancient CMB. Some called it a cosmic tension, a hint that dark energy might not be constant, as Einstein's cosmological constant suggested, but something far more dynamic. Could it evolve over time? Could its strength have changed since the dawn of creation? These questions send chills down the spines of cosmologists, because if dark energy isn't what we thought, we might need to rewrite the rules of physics itself. The beauty of Planck's findings lies in their duality. They confirmed dark energy's existence with overwhelming evidence, yet also exposed gaps in our understanding. Those faint temperature variations are more than relics. They're active puzzles, whispering secrets about the universe's first moments. And just like a detective piecing together a crime scene, scientists are using these clues to reconstruct how dark energy emerged from the cosmic chaos. Was it always woven into space itself, or did it awaken later, like a sleeping giant reshaping the cosmos? Every new analysis brings us closer to answers and deeper into the mystery. Now, let's zoom in on another cosmic detective tool, one that turns the universe's very structure into a measuring tape. Imagine the early cosmos as a bubbling soup of particles, where sound waves rippled through the hot, dense plasma like echoes in a cavern. These weren't ordinary sound waves, though. They were baryon acoustic oscillations, pressure-driven vibrations that left permanent scars on the universe as it expanded and cooled. Fast forward 13.8 billion years, and those ancient ripples are still etched into the sky, frozen in the distribution of galaxies like cosmic breadcrumbs. Here's how scientists used them when those primordial waves finally stalled their energy sapped by the universe's expansion. They left behind a telltale pattern. Galaxies today are slightly more likely to be separated by a specific distance, roughly 500 million light-years apart. That's the standard ruler astronomers rely on. Projects like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument, or DESI, map millions of galaxies to spot this faint fingerprint. By measuring how this ruler stretches over cosmic time, researchers can track dark energy's grip on space itself. What's astonishing is how perfectly this method dovetails with supernova data. While exploding stars reveal the universe's acceleration, Baryon oscillations reveal how space stretches, like comparing a speedometer to an odometer. And the results are uncanny. Both point to dark energy's dominance, but with a twist. When DESI latest data revealed the universe's expansion rate didn't quite match earlier predictions, it reignited debates. Could dark energy be changing strength, or is there some hidden ingredient we've yet to account for? The real power of these oscillations lies in their sheer scale. Unlike supernova, which are fleeting events, Baryon patterns are woven into the cosmos's fabric. They're a fossil record of the universe's youth, offering a cross-check so precise it's reshaped our confidence in dark energy. Yet every answer deepens the mystery. Why does this invisible force leave such a crisp imprint on galactic distances? And if it's truly constant, why do some measurements still disagree? The more we measure, the more the universe seems to whisper, "There's something bigger here, keep looking." But here's where things get really strange. Even with all these brilliant tools, supernova, Baryon oscillations, the cosmic microwave background, scientists keep hitting the same baffling wall. When they measure how fast the universe is expanding today, different methods give different answers. It's called the Hubble constant tension, and it's like trying to solve a puzzle where two pieces stubbornly refuse to fit. On one side, you have the Planck satellite's ultra-precise measurements of the early universe's expansion, inferred from the CMB. On the other, you have modern telescopes like Hubble and Gaia, tracking the motions of nearby stars and galaxies to gauge today's expansion rate. Both methods are meticulous, both backed by mountains of evidence, yet they disagree by about 7%. A gap that might sound small, but in cosmology, it's a chasm. What could explain this cosmic mismatch? One tantalizing possibility is that dark energy isn't the static force Einstein imagined. Maybe it's evolved over time, growing stronger or weaker as the universe aged. Think of it like a dimmer switch on a light. What if dark energy's influence isn't fixed but adjustable? Some theories even suggest it could interact with dark matter, the universe's other great mystery, in ways we haven't yet imagined. Or perhaps there's an entirely new particle or field at play, something beyond the standard model of physics. The stakes couldn't be higher. If dark energy is dynamic, it would upend decades of cosmological models. Imagine rewriting the universe's entire history because one number didn't add up. That's why teams around the world are racing to resolve this tension, building ever more precise instruments like the James Webb Space Telescope and the upcoming Vera Rubin Observatory. Every new observation tightens the screws on this puzzle, forcing us to ask, are we missing a fundamental piece of reality? Or is the universe simply messing with us, dangling clues just out of reach? What makes this debate so electrifying is how it pits cosmic eras against each other. Planck's data captures the universe's infancy, while Hubble's measurements reflect its present-day behavior. If they can't agree, it suggests something profound changed in between, something our current physics can't explain. Maybe dark energy didn't just nudge the cosmos apart, maybe it rewrote the rules along the way. For now, the tension remains, a quiet hum in the background of every cosmological conference. But history tells us this much: when the numbers don't add up, that's usually when the biggest discoveries are waiting to be made. What if the greatest cosmic mystery isn't a mysterious force at all, but a flaw in our understanding of gravity itself? That's the provocative question at the heart of modified gravity theories, where dark energy might not exist. Instead, gravity could play by different rules on the vast scales of the universe, bending space-time in ways Einstein never predicted. It's a radical idea, but one that's gained traction among some physicists tired of chasing invisible energy. Take modified Newtonian dynamics as the most famous challenger. Proposed in the 1980s by physicist Mordechai Milgrom, Mund suggests that gravity doesn't weaken as quickly over large distances as Newton or Einstein claimed. Instead, it tapers off more gently, mimicking the effects we've attributed to dark energy. Picture a car that mysteriously speeds up even when you ease off the gas. Dark energy says someone's pressing a hidden pedal. Mund argues the engine's just wired differently. At first glance, it's an elegant solution. After all, why invent an unknown force if tweaking the known ones could explain galactic motions? But here's where the debate gets fierce. While Mund neatly explains some anomalies like why stars at the edges of galaxies orbit faster than expected, it stumbles when faced with the universe's grandest puzzles. The cosmic microwave background's intricate patterns, for instance, align perfectly with dark energy models but leave Mund scrambling. Then there's the bullet cluster, two colliding galaxies where gravitational lensing reveals mass separated from visible matter. Dark energy and dark matter theories predicted this. Mund not so much. Still, proponents aren't backing down. Newer versions of modified gravity, like tensor vector scalar theories, attempt to patch these holes by adding layers of complexity. Yet each adjustment risks making the theory less elegant than the problem it's trying to solve. Meanwhile, dark energy's case grows stronger with every supernova survey and baryon oscillation map. The irony, even if Mund fails, its existence pushes cosmologists to test dark energy more rigorously. After all, the best scientific ideas thrive under fire. So where does that leave us? For now, dark energy remains the reigning explanation, but the very existence of this debate is a triumph. It shows science at its best, unafraid to question even its most cherished assumptions. Maybe one day we'll find gravity really does bend the rules, or maybe dark energy will reveal stranger truths. Either way, the universe keeps us guessing. Here's a mind-bending thought. What if the key to dark energy lies in the very fabric of nothingness? Not the empty void we imagine, but a seething, bubbling quantum foam where particles flicker into existence and vanish in fractions of a second. This isn't just theoretical poetry. It's the reality of quantum vacuum fluctuations, where so-called empty space crackles with unimaginable energy. And some physicists believe this ceaseless dance of virtual particles could be the hidden engine behind dark energy's cosmic push. But there's a colossal problem, one so glaring it's been dubbed the worst prediction in physics. When scientists calculate how much energy these quantum fluctuations should contribute to the universe, the numbers are laughably off. We're talking 10 to the power of 120 times stronger than what we actually observe. That's a 1 followed by 120 zeros, a discrepancy so vast it's like predicting a teacup could hold all the water in the oceans. How could reality be so wildly out of sync with theory? The roots of this puzzle stretch back to the birth of quantum mechanics. Even in a perfect vacuum, particles and antiparticles spontaneously emerge, borrowing energy from the universe for fleeting moments before annihilating each other. These fleeting disturbances create a background hum of energy. Think of it as the universe's static noise. Einstein's equations suggest this vacuum energy should act just like dark energy, exerting a repulsive force on spacetime itself. But the numbers refuse to cooperate. Why does this matter? Because if quantum vacuum energy were even a fraction as strong as predicted, the universe would have ripped itself apart before stars or galaxies could form. The fact that we exist at all implies something's either canceling out this energy or our understanding of quantum fields is fundamentally incomplete. Some theorists propose exotic solutions like hidden symmetries that neutralize most of this energy, leaving behind just the faint whisper we call dark energy. Others wonder if we're misreading quantum mechanics entirely, like trying to measure a tidal wave with a rain gauge. The irony is delicious. The same quantum physics that brilliantly explains subatomic particles fails spectacularly when scaled up to the cosmos. Yet this very failure might point the way forward. New theories like supersymmetry attempt to bridge the gap by predicting undiscovered particles that could balance the equations. Meanwhile, experiments with ultra-precise lasers and Casimir effect measurements are probing the vacuum's energy in labs, hunting for clues. What's at stake isn't just a tweak to the math, it's a potential revolution. If vacuum fluctuations truly connect to dark energy, we might uncover a hidden link between the quantum realm and cosmic expansion, unifying physics' greatest scales. Or perhaps the universe is telling us that empty space isn't empty at all, but a dynamic stage where deeper laws are waiting to be discovered. Either way, the quantum foam keeps bubbling and the mystery only deepens. Einstein's so-called biggest blunder might actually be his most accidental triumph. Back in 1917, when he first scribbled that tiny Greek letter lambda into his equations, he wasn't thinking about dark energy. He was just trying to keep the universe from collapsing under its own gravity. At the time, astronomers believed the cosmos was static, neither expanding nor contracting, and Einstein's general theory of relativity kept predicting it should be doing one or the other. So he added a fudge factor, a cosmological constant, to balance the scales. Then, when Edwin Hubble proved the universe was expanding, Einstein tossed lambda aside, calling it unnecessary. But here's the twist: nearly a century later, that same constant might be the perfect description of dark energy's relentless push. Why does this simple term, just a number, really still dominate the conversation? Because it fits the data eerily well. Imagine dark energy as an inherent property of space itself. The more space expands, the more dark energy there is, creating a feedback loop that drives acceleration. That's exactly what the cosmological constant represents. Energy woven into the vacuum, unchanging and eternal. No exotic particles, no undiscovered fields, just spacetime's own stubborn refusal to sit still. When astronomers measure supernova or baryon oscillations, lambda's predictions align almost perfectly. It's the Occam's razor of cosmic explanations, the simplest solution that works. But simple doesn't mean satisfying. For some scientists, the cosmological constant feels like a cosmic cop-out. If lambda is real, why is its value so impossibly tiny compared to quantum physics predictions? Tweak it even slightly, and the universe either expands too fast for stars to form or collapses before life can emerge. This fine-tuning problem stings. It makes our existence seem like a bizarre statistical fluke. Others argue lambda is too passive. If dark energy truly is constant, why did it let gravity dominate for billions of years before suddenly taking over? A dynamic universe demands a dynamic explanation, not a static number frozen in time. The debate splits cosmology down the middle. On one side, traditionalists champion lambda as the cleanest answer, flaws and all. On the other, rebels hunt for alternatives, quintessence fields that evolve, extra dimensions leaking gravity, even holographic principles where our universe is a projection of deeper physics. Yet every time a new theory emerges, lambda outlasts it, clinging on like a stubborn fact. Maybe that's the lesson here. Sometimes the universe's deepest truths hide in plain sight, disguised as mistakes. Einstein's blunder might not be the final word on dark energy, but for now, it's the one we can't ignore. Picture a universe where dark energy doesn't just nudge galaxies apart, it grows stronger, fiercer, until its grip becomes unstoppable. This isn't just an acceleration, it's a runaway train where space itself stretches faster than light can cross it. Welcome to the most extreme fate cosmologists have dreamed up, the Big Rip, a scenario so violent it would shred reality at every scale. And at the heart of this cosmic horror story lies a hypothetical monster called phantom energy. What makes phantom energy so terrifying? Unlike the gentle, constant push of Einstein's cosmological constant, phantom energy amplifies over time. Imagine a rubber band that doesn't just stretch, it snaps harder the farther you pull. In this case, the rubber band is space-time, and the snapping force grows until nothing can withstand it. First, galaxy clusters would be ripped apart, flung into the void, then individual galaxies, then stars, planets, and finally, in the last fraction of a second, atoms themselves would be torn asunder. The universe wouldn't just fade into cold emptiness, it would dissolve in a crescendo of destruction. But here's the catch. Phantom energy isn't just speculative, it defies some of physics' most cherished rules. For one, it violates the so-called null energy condition, a bedrock principle that says energy can't behave in ways that make gravity repulsive beyond a certain limit. Phantom energy laughs at that limit. It's the equivalent of a car accelerating so fast its speedometer breaks, except in this case, the speedometer is the fabric of reality. So is there any evidence for such a radical idea? Surprisingly, yes, or at least the data doesn't rule it out. When scientists analyze supernova and baryon acoustic oscillations, most results align with a constant dark energy. But a few outliers hint at something darker. In 2018, a study of 700 supernova found slight deviations suggesting dark energy's strength might be increasing. The statistical significance was weak, but it was enough to send a shiver through the cosmology community. Critics, though, are quick to point out the flaws. If phantom energy were real, its effects should already be visible in the cosmic microwave background's delicate patterns. Yet Planck's data shows no sign of such extreme behavior. Then there's the theoretical headache. Phantom energy could allow for time travel paradoxes and unstable quantum vacuums, turning physics into a free-for-all. As one researcher put it, the universe would have ripped itself apart long before life could exist if phantom energy were even slightly stronger. Yet the idea persists because it forces us to confront a deeper question. How well do we really understand dark energy's nature? The Big Rip might be the most dramatic possibility, but it's not the only one where dark energy evolves. Quintessence models, for example, propose a dynamic field that could weaken or strengthen over time without triggering doomsday. Others suggest phantom energy might only activate in the distant future, leaving our cosmic neighborhood untouched for billions of years. What's fascinating is how this debate mirrors humanity's oldest fears and fascinations. Every culture has its apocalypse myths of floods, fires, frosts. The Big Rip is simply the latest version, written in the language of equations and redshift data. And while the odds may favor a quieter cosmic fate, the mere possibility reminds us how much we still have to learn. After all, if dark energy can accelerate the universe, who's to say it can't one day turn predator? Until we know for sure, the phantom lingers a shadow at the edge of our equations, waiting to rewrite the end of everything. Imagine a universe where reality isn't just the 3 dimensions we see, but 10 or even 11, curled up so tightly we'd never notice. This isn't science fiction, it's the heart of string theory, one of the most ambitious ideas in physics, and hidden within its labyrinth of equations might lie the answer to dark energy's deepest secrets. String theory proposes that everything in existence, every particle, every force, is made of tiny, vibrating strings. These strings don't just dance in the dimensions we know, they resonate through hidden ones, folded into the fabric of space itself. Some versions of the theory predict that dark energy emerges naturally from these extra dimensions, like echoes in a cosmic canyon. One particularly compelling idea, called the KKLT scenario, suggests dark energy could arise from the way these dimensions stabilize themselves, creating a repulsive force that drives cosmic acceleration. But here's the catch: string theory isn't just one idea. It's a landscape of possibilities with 10 to the power of 500 potential universes, each with its own laws of physics. In some, dark energy might be strong, in others, weak or non-existent. This multiverse concept raises a staggering question. If countless universes exist, is ours just an accident, one where dark energy's value happens to allow galaxies and life to form? Or is there a deeper principle at work, selecting for universes like ours? Testing these ideas is where things get thorny. String theory operates at energy scales so high we'd need a particle accelerator the size of a galaxy to probe them directly. Without experimental proof, the theory risks floating in the realm of pure mathematics, beautiful but untethered from reality. Yet some scientists aren't giving up. They're hunting for indirect clues, like subtle imprints of extra dimensions in gravitational waves or anomalies in particle collisions. Others are exploring the swampland conjecture, a set of mathematical constraints that might rule out certain string theory models, including some that predict dark energy. The real irony: string theory was born to unify physics, but dark energy might be its toughest challenge yet. If the theory can't explain why dark energy is so bafflingly weak compared to predictions, it might need a radical rethink. Or perhaps dark energy is the key that finally unlocks string theory's secrets, bridging the gap between the quantum world and the cosmos. For now, the connection remains a tantalizing maybe, a cosmic puzzle wrapped in extra dimensions, waiting for its next clue. Right now, as galaxies drift further apart in the cosmic dark, two colossal projects are gearing up to hunt for the fingerprints of dark energy like never before. The Dark Energy Spectroscopic Instrument, or DESI, perched atop a mountain in Arizona, isn't your average telescope, it's a cosmic cartographer on steroids. With 5,000 robotic eyes, it can simultaneously capture light from millions of galaxies, quasars, and stars, stitching together the largest three-dimensional map of the universe ever made. But here's the real magic. By measuring how Barrian acoustic oscillations, those ancient sound wave fossils, stretch across different eras, DESI isn't just observing dark energy's effects. It's trying to catch it red-handed, changing over time. Meanwhile, halfway across the globe in Chile's bone-dry Atacama Desert, the Vera Rubin Observatory's Legacy Survey of Space and Time, or LSST, is preparing to unleash an entirely different kind of power. Equipped with the world's largest digital camera, a 3.2 gigapixel behemoth, it will scan the entire southern sky every few nights, spotting subtle changes in brightness that might betray dark energy's secrets. While DESI focuses on precise galaxy positions, LSST's strength lies in spotting gravitational lensing, where dark energy's push warps the very fabric of space-time, bending light from distant objects like a funhouse mirror. Together, these projects form a 1-2 punch against the mystery. DESI ultra-precise maps could reveal whether dark energy's strength has varied over billions of years, a smoking gun for dynamic theories like quintessence. LSST, on the other hand, might uncover how dark energy warps the universe's large-scale structure, offering clues about whether it interacts with dark matter or even unknown particles. But the most tantalizing possibility, they might finally resolve the Hubble tension, that nagging mismatch in cosmic expansion rates by exposing gaps in our current models. What makes this next chapter so thrilling is the sheer scale of data. DESI will catalog 40 million galaxies and quasars, while LSST will image 20 billion galaxies over a decade. That's not just more information, it's a tidal wave of it, demanding supercomputers and machine learning to sift through the noise. And hidden in those numbers could be the answer to one of science's greatest riddles. Is dark energy the steady hand of Einstein's cosmological constant, or is it a shape-shifter, evolving as the universe ages? The stakes couldn't be higher. If dark energy isn't constant, everything from the fate of galaxies to the very laws of physics might need rewriting. DESI and LSST aren't just tools, they're time machines, letting us watch the universe's expansion in ultra-high definition across eons. And if they find even a hint that dark energy is changing, that's when the real revolution begins. Of all the universe's elusive particles, none are quite as ghostly as neutrinos, tiny, nearly massless entities that zip through space, passing through planets and people alike as if they weren't even there. Billions stream through your fingertips every second, leaving no trace. Yet despite their faint presence, these cosmic phantoms might hold unexpected sway over dark energy's grand narrative. The connection lies in neutrinos' bizarre properties. Born in the hearts of stars, supernova, and even the Big Bang itself, they barely interact with matter, making them notoriously difficult to detect. But here's the twist. Though individually insignificant, their collective mass spread across trillions of particles could subtly warp spacetime's expansion. Picture a vast, invisible sea of these particles, gently tugging at the fabric of the cosmos, their combined gravity either amplifying or countering dark energy's push. The math is delicate. If neutrinos have even a smidge more mass than we've measured, their gravitational influence might alter how fast galaxies drift apart. That's where experiments like IceCube and Dune come in. Buried deep beneath the Antarctic ice, IceCube isn't a typical telescope, it's a neutrino hunter, using thousands of sensors to catch the rare flashes of light produced when a neutrino finally, against all odds, collides with an atom. By mapping these collisions, scientists can trace neutrinos' paths back to their violent origins, piecing together how much energy, and therefore mass, they carry. Meanwhile, the Deep Underground Neutrino Experiment, or DUNE, will shoot beams of these particles through 800 miles of Earth, studying how they oscillate between different flavors. Each oscillation is a clue, revealing nuances about their mass that could reshape our dark energy equations. Why does this matter? Because neutrinos are the wild card in cosmic expansion. If they're heavier than we think, they might slow dark energy's acceleration ever so slightly, like throwing sand into a finely tuned engine. Alternatively, some theories suggest high-energy neutrinos could interact with dark energy fields in ways we've yet to imagine, perhaps even transferring energy to them. It's a long shot, but in a mystery this profound, every thread counts. What's fascinating is how these experiments turn weakness into strength. Neutrinos' reluctance to interact makes them cosmic messengers, carrying information from the universe's most violent events straight to our detectors. No distortion, no interference. By decoding their secrets, we might uncover hidden links between particle physics and cosmology, bridging scales from the infinitesimal to the infinite. And if neutrinos do influence dark energy, it would mean the universe's fate isn't dictated by one force alone, but by a delicate dance of the seen and unseen. For now, the data is still coming in, each new neutrino collision a potential Rosetta Stone. Whether they're bit players or key architects of cosmic expansion, one thing's certain: in the hunt for dark energy's secrets, even the faintest whispers can reshape the story. If you want to see dark energy in action, don't look at the galaxies, look at the nothingness between them. Cosmic voids, the universe's emptiest regions, aren't just blank spaces. They're colossal laboratories where dark energy's influence shines brightest. Picture bubbles of near-total vacuum, some spanning hundreds of millions of light-years, where galaxies are so sparse you could cross one and never see a single star. Yet these vast deserts hold a crucial secret. They expand faster than the densest galaxy clusters, as if dark energy gets an extra grip on emptiness. Why does this happen? Think of the universe as a stretchy rubber sheet, where matter clusters like around galaxies' gravity pulls the sheet taut, resisting dark energy's push. But in voids, there's hardly any matter to fight back, so space stretches more easily. It's like blowing up a balloon with weak spots. The emptiest areas inflate fastest. This difference isn't just subtle. Recent surveys like EBOS and the Dark Energy Survey have measured voids expanding up to 20% quicker than dense regions. That mismatch is a smoking gun, revealing dark energy's strength in ways supernova or baryon oscillations can't. But here's where it gets even wilder. Voids aren't passive. As they grow, their edges become cosmic construction zones where galaxies pile up like foam on a wave. By mapping these void walls, astronomers can trace how dark energy sculpts the universe's large-scale structure. Projects like the upcoming Euclid Space Telescope plan to chart millions of voids in 3D, turning their growth patterns into a precision test for dark energy theories. If Einstein's cosmological constant is correct, voids should expand at a predictable rate. But if dark energy fluctuates, say, in quintessence models, voids might reveal unexpected twists in spacetime stretching. The real power of voids lies in their sheer scale. While supernova are fleeting and baryon oscillations are subtle, voids are giants, imprinting dark energy's signature across billions of years. They're also eerily symmetrical, making their distortions easier to measure than the tangled web of galaxy filaments. Some researchers even speculate that voids could help solve the Hubble tension, since their expansion rates offer an independent check on the universe's current growth spurt. Yet voids come with their own puzzles. Why do some stretch faster than others? Could their shapes hint at dark energy's interaction with dark matter? And if voids are truly the universe's fastest expanding regions, what does that mean for the far future? One chilling possibility: as voids grow, they might one day isolate galaxy clusters like islands in an ever-widening sea, cutting them off from the rest of the cosmos. For now, though, these vast nothings are giving us something priceless: a front-row seat to dark energy's most dramatic effects. What if the universe we live in shouldn't exist, at least according to the deepest laws of physics? That's the bombshell at the heart of the swampland conjecture, a set of mathematical rules emerging from string theory that threatens to upend everything we think we know about dark energy. Picture this: string theory, the leading framework for unifying all forces of nature, might have a built-in filter, a cosmic bouncer, if you will, that kicks out certain types of universes, including ones with stable dark energy like ours. It's as if we've been handed a ticket to a party we're not supposed to attend. The controversy centers on a deceptively simple question: can dark energy truly be constant, as Einstein's cosmological constant suggests? String theorists argue no. Their calculations hint that stable universes require dark energy to evolve over time or interact with other fields, not sit idly like a fixed background actor. The so-called swampland is the mathematical no-go zone where theories look plausible at first glance but can't actually describe a consistent, functioning cosmos. And guess what? A universe with a perfectly unchanging dark energy might be stuck right in that swamp. This isn't just academic nitpicking. If the swampland conjecture holds, it would mean the cosmological constant, the reigning explanation for dark energy, is fundamentally flawed. Instead of lambda being a static number, dark energy might need to be dynamic, like a field called quintessence that shifts and adapts over billions of years. The implications are staggering. It would mean dark energy isn't an immutable property of space, but something far more alive, interacting with the cosmos in ways we've yet to imagine. Critics, though, aren't ready to toss out lambda just yet. They point out that the swampland's mathematical boundaries are still fuzzy, more like guidelines than ironclad laws. After all, our universe does exist, cosmological constant, and all, so if string theory says that's impossible, maybe string theory needs adjusting. Others suggest the swampland might allow for loopholes, like temporary periods where dark energy appears constant before revealing its true nature. The real tension here is between elegance and observation. String theory seeks beautiful, self-consistent equations, but the universe isn't obligated to care about our aesthetic preferences. Right now, the data favors a constant dark energy, yet the swampland whispers that we might be missing a deeper layer. Future experiments, like precision measurements of the universe's expansion or subtle shifts in the cosmic microwave background, could tip the scales. Either they'll expose cracks in lambda's facade, or they'll force string theorists to rethink their most cherished principles. What makes this debate so electrifying is what it reveals about science itself. Sometimes the most profound discoveries come not from confirming our ideas, but from finding places where the math and the universe refuse to agree. Whether the swampland is a dead end or a roadmap to new physics, one thing's clear: dark energy still has surprises in store, and the next clue might be hiding in the equations we haven't dared to solve yet. The idea of a constant dark energy is comforting, a predictable force woven into the fabric of space, unchanging since the dawn of time. But what if that's not the whole story? What if dark energy is more like a shapeshifter, growing stronger or weaker as the universe ages? This isn't just speculation. It's the heart of one of cosmology's most tantalizing possibilities: time-varying dark energy. Imagine a cosmic dimmer switch, slowly turning up or down over billions of years, altering the fate of everything in its wake. The clues are already hiding in plain sight. When astronomers compare the universe's expansion rate today with ancient signals like the cosmic microwave background, the numbers don't quite match up. It's as if dark energy's influence wasn't always the same. Maybe it started as a whisper and grew into a roar, or perhaps it's fading away unnoticed. If true, this would rewrite the rules of cosmology overnight. Einstein's cosmological constant would be out. A dynamic, evolving force would take its place. Enter missions like Euclid and JWST, the next generation of cosmic detectives. Euclid, the European Space Agency's flagship dark energy hunter, isn't just mapping galaxies, it's building a time-lapse of the universe's expansion across 10 billion years. By measuring how light bends around massive galaxy clusters, a phenomenon called weak gravitational lensing, it can spot subtle changes in dark energy's grip on spacetime. JWST, NASA infrared powerhouse, takes a different approach, scanning thousands of supernova to see if dark energy's acceleration has shifted over cosmic epochs. Together, they're not just testing whether dark energy varies, they're asking how and why. The implications are staggering. If dark energy is weakening, the universe might eventually slow its runaway expansion, avoiding a cold, lonely fate. If it's strengthening, the Big Rip scenario where galaxies, stars, and even atoms are torn apart becomes terrifyingly plausible, but the real shocker: time-varying dark energy could hint at entirely new physics. Some theories suggest it might be tied to an undiscovered field like quintessence, which evolves like a cosmic weather system. Others propose it's interacting with dark matter in ways we've yet to imagine. Critics argue the evidence for variation is still thin statistical noise, not a breakthrough. But with every new dataset, the puzzle deepens. Recent analyses of supernova and baryon acoustic oscillations have found faint hints that dark energy strength might not be so constant after all. The numbers are too tentative to call it a discovery, but they're enough to keep scientists awake at night. After all, the history of cosmology is littered with impossible ideas that turned out to be true. The beauty of this mystery is how it turns the universe into a living laboratory. If dark energy changes over time, it means the cosmos isn't just expanding, it's transforming, governed by laws we're only beginning to glimpse. Missions like Euclid and JWST aren't just tools, they're time machines letting us watch dark energy's story unfold across the ages, and if they find even a whisper of variation, that's when the real adventure begins. Here's a chilling thought: what if dark energy's bizarrely perfect strength isn't a cosmic accident, but just one roll of the dice in an infinite multiverse? Imagine countless universes bubbling into existence, each with its own random value for dark energy, some so weak they collapse instantly, others so strong they tear themselves apart before stars can form. Ours just the lucky lottery ticket where the numbers lined up just right for galaxies, planets, and life to emerge. This isn't just speculative physics, it's the controversial heart of the Anthropic principle, where cosmology collides head-on with philosophy. The argument hinges on a single, haunting observation. Dark energy's measured value is absurdly small compared to theoretical predictions, so tiny it's like balancing a grain of sand against the weight of a mountain. If it were even slightly stronger, galaxies would never have formed. Slightly weaker, and the universe would have crumpled back into a black hole eons ago. Such razor-thin fine-tuning seems impossible unless our universe isn't special, just survivable. In this view, we only perceive dark energy's perfect strength because we're here to observe it. Other universes with hostile values, they're empty, lifeless, and unseen. String theory lends eerie support to this idea. Its landscape of possible solutions suggests a mind-boggling 10 to the power of 500 unique vacuum states, each representing a universe with different constants. Dark energy's value in our universe might simply be the one that allowed complexity to arise. No deeper reason, no elegant equation, just dumb luck on a cosmic scale. Critics, though, recoil at this explanation, calling it science stopping. They argue it swaps testable physics for untestable metaphysics. After all, if every possible universe exists, how could we ever falsify the theory? Yet the multiverse hypothesis isn't entirely unfalsifiable. Some researchers propose hunting for bruises in the cosmic microwave background, imprints left by collisions with other bubble universes in our distant past. Others suggest that if our universe's laws are maximally life-friendly, not just barely survivable, it could hint at a deeper principle beyond randomness. The debate splits scientists down the middle. Nobel laureate Steven Weinberg once called the anthropic reasoning a bitter pill, while others, like Leonard Susskind, embrace it as the only way to make sense of dark energy's quirks. What's at stake isn't just dark energy's origin, it's the soul of scientific inquiry. If we accept the multiverse, do we risk giving up on finding a fundamental theory? Or is it the ultimate Copernican revolution, dethroning our universe from cosmic privilege? For now, the question lingers at the edge of physics, where hard data blurs into profound speculation. Maybe dark energy's fine-tuning is a clue, not just to hidden dimensions or new fields, but to a reality far vaster and stranger than we ever imagined. Black holes, those cosmic monsters that swallow light whole, might be hiding one of dark energy's best-kept secrets. It sounds like science fiction, but a bold new theory suggests these gravitational behemoths aren't just devouring matter. They could be storing vacuum energy, the very fuel powering the universe's runaway expansion. Picture this, deep within a black hole's event horizon, where space-time bends into oblivion, quantum fluctuations might be pooling into an invisible reservoir, subtly feeding dark energy's grip on the cosmos. If true, it would mean the universe's most destructive force and its most mysterious are two sides of the same coin. This audacious idea stems from a cosmic coincidence too striking to ignore. When physicists calculate the total vacuum energy stored in all the black holes across the universe, the numbers eerily align with independent measurements of dark energy's density. It's as if someone left a trail of breadcrumbs between two seemingly unrelated phenomena, one that crushes stars into singularities, the other that stretches space itself. The math isn't just suggestive, it's provocative, hinting that black holes might act like cosmic batteries, charging dark energy with every particle they consume. But how could a force that repels galaxies emerge from the ultimate gravitational traps? The key lies in the quantum vacuum. Black holes aren't just empty pits. They're seething with virtual particles popping in and out of existence, thanks to Heisenberg's uncertainty principle. Normally, these fluctuations cancel each other out, but near a singularity, spacetime's extreme curvature might disrupt the balance, trapping excess energy. Over billions of years, as black holes grow by feeding on stars and gas, this stored vacuum energy could leak into the universe, subtly fueling its acceleration. It's a cosmic recycling program on the grandest scale. Devour matter here, amplify dark energy there. Critics, though, aren't sold. For one, the theory hinges on speculative quantum gravity effects we can't yet observe. Black holes' interiors are famously unknowable, their secrets locked behind an event horizon no signal can escape. And if black holes truly fed dark energy, their growth should correlate with the universe's expansion rate, a claim that's still hotly debated. Some astrophysicists argue that supermassive black holes at galactic centers are too rare to account for dark energy's omnipresent push, while others counter that even small, ancient black holes from the early universe could collectively hold the missing energy. The most tantalizing evidence comes from recent observations of ancient black holes. Surveys like the Sloan Digital Sky Survey have found that supermassive black holes in the early universe were oddly overweight, far larger than expected for their age. If these giants grew by absorbing vacuum energy alongside matter, it could explain both their size and dark energy's prevalence. Meanwhile, gravitational wave detectors like LIGO are hunting for mergers of intermediate black holes, whose properties might reveal if they carry extra energy locked within their cores. What makes this theory so electrifying isn't just its potential to solve two puzzles at once, it's the sheer irony. Black holes, long seen as the universe's ultimate destroyers, might secretly be its architects, shaping the cosmos not just through gravity, but through an invisible partnership with dark energy. Future telescopes, like the European Space Agency's LISA mission, could test this by measuring how black hole mergers ripple space-time, searching for anomalies that betray hidden energy reserves. For now, the idea remains a thrilling, what-if a reminder that in cosmology, the wildest guesses often lead to the deepest truths. Whether black holes are dark energy's secret keepers or just another cosmic red herring, one thing's certain: the universe loves a good plot twist. And this one might rewrite the story of everything. The Hubble tension isn't just a minor disagreement, it's a full-blown cosmic standoff, pitting the universe's early days against its present behavior, with dark energy caught squarely in the middle. On one side, we have the pristine afterglow of the Big Bang, the cosmic microwave background, telling us how fast space was stretching nearly 14 billion years ago. On the other, modern telescopes like Hubble and Gaia track galaxies and supernova to measure today's expansion rate. The problem? These two methods refuse to agree, differing by about 7%, a gap that's persisted despite decades of ever sharper observations. This discrepancy might seem small, but in cosmology, it's a glaring red flag. If our measurements are correct, the universe isn't just expanding, it's doing so faster than the early conditions should allow. One tantalizing explanation: dark energy didn't wait politely for galaxies to form before flexing its influence. Instead, it might have stirred earlier than we assumed, subtly tweaking the cosmos's growth in ways that now echo across billions of years. The evidence for this audacious idea comes from unexpected corners. Take the Dark Energy Survey's detailed maps of galaxy clustering. When researchers compared these patterns to predictions based on the cosmic microwave background, they found hints that dark energy's repulsive push might have been at work even during the universe's adolescence, gently nudging matter apart before it fully took center stage. Then there's the puzzling behavior of ancient quasars, whose light appears slightly dimmer than standard models predict, another whisper that expansion could have accelerated sooner. Critics, though, aren't ready to rewrite the textbooks. They argue that systematic errors, tiny biases in how we measure supernova or calibrate telescopes, could still explain the tension without invoking early dark energy. Others suggest exotic dark matter interactions or undiscovered particles might be muddying the waters, but the most provocative counterpoint comes from theorists who propose that dark energy isn't a single force at all, but a spectrum of phenomena that evolved over time, leaving fragmented clues across cosmic history. The stakes here are astronomical. If dark energy truly woke up earlier than expected, it would mean our universe's expansion story is far more dynamic and chaotic than the smooth narrative we've long assumed. It could imply that dark energy isn't a constant backdrop but an active player, responding to the cosmos's changing conditions like a chameleon shifting colors. Future missions like the Nancy Grace Roman Space Telescope aim to settle the debate by peering back to an era when dark energy's influence should have been negligible, if standard models hold. But if Roman finds even a trace of its fingerprint in the young universe, that's when cosmology's rulebook gets tossed out the window. What makes this debate so gripping is how it forces us to confront the limits of our cosmic storytelling. The Hubble tension isn't just a numbers game. It's a clash of eras, a tug of war between the universe's first light and its present-day rhythms. And if dark energy's role is more complex than we imagined, it might mean the cosmos has been quietly rewriting its own rules all along, hiding its true nature in plain sight. Imagine a star so dense it bends light like a black hole, yet harbors no crushing singularity at its core, just a swirling vortex of pure vacuum energy, the same force accelerating the universe's expansion. These aren't science fiction, they're dark energy stars, one of the most radical ideas in modern astrophysics. Proposed by physicist George Chaplin in the early 2000s, these hypothetical objects blur the line between star and cosmic anomaly, offering a tantalizing alternative to the black holes we thought we knew. What sets dark energy stars apart? Picture a collapsing star so massive that conventional physics says it should form a black hole, but instead of pinching into a singularity, its core transforms. Quantum fluctuations in the vacuum, those same eerie particles popping in and out of existence, become so intense they halt the collapse entirely. The result? A superdense shell of matter hovering just outside what would have been an event horizon, concealing a bubbling core of dark energy. From the outside, it looks nearly identical to a black hole. Light bends around it, matter spirals into its grasp, time slows to a crawl near its surface. But inside, the rules of space-time might play out very differently. The real magic lies in how these stars could solve some of black holes' thorniest paradoxes. Take the infamous information loss problem, the idea that anything falling into a black hole vanishes forever, violating quantum mechanics' insistence that information can't be destroyed. Dark energy stars sidestep this entirely. Since they lack singularities, information could theoretically escape, preserved in the chaotic swirl of vacuum energy at their hearts. Then there's the firewall paradox, where black holes' event horizons should blaze with lethal radiation. Dark energy stars offer a cleaner solution. No horizon, no firewall, just an exotic boundary where physics gets weird but stays consistent. So how would we spot one? The differences are subtle but detectable. When black holes merge, they unleash gravitational waves with a distinctive ring-down signal, a fading chirp as the new black hole settles into shape. Dark energy stars, though, might produce echoes in these waves, faint ripples betraying the absence of an event horizon. Telescopes like LIGO and Virgo are already hunting for these anomalies. Another clue could come from accretion disks, the superheated rings of matter circling black holes. Dark energy stars might warp these disks in peculiar ways, their lack of a true horizon altering how light escapes. But the most intriguing possibility, some of the black holes we've already found might actually be dark energy stars in disguise. Take Sagittarius, a star, the supermassive beast at our galaxy's center. Its behavior aligns with black hole predictions, but so would a dark energy star's. Only ultra-precise measurements, like tracking stars orbiting perilously close, could reveal tiny deviations in spacetime's warp that betray its true nature. Critics argue the theory stretches plausibility. Maintaining a stable dark energy core requires exotic physics we've never observed, and the math is notoriously slippery. Yet supporters counter that dark energy stars elegantly unite two cosmic mysteries, black holes and vacuum energy, into a single, testable framework. Whether they exist or not, these phantom stars force us to rethink the most extreme objects in the universe. After all, if dark energy can push galaxies apart, why couldn't it also hold a star's corpse from collapsing? The answer might be hiding in plain sight, masquerading as the universe's darkest secrets. The cosmic microwave background should be a perfect, random mosaic, a snapshot of the universe's fiery infancy with fluctuations scattered like paint splatters on a canvas. But when scientists stared deep into this ancient light, they found something unsettling. A bizarre alignment of hot and cold spots stretching across the sky like a cosmic axis. A pattern so improbable it earned the ominous nickname, the Axis of Evil. This isn't just a statistical fluke, it's a full-blown anomaly, suggesting the universe might be fundamentally lopsided, and dark energy could be the invisible hand behind the tilt. At the heart of the mystery lies the CMB's quadrupole and octopole, moments fancy terms for how its temperature variations are distributed. Instead of being randomly oriented, these patterns seem to line up along a preferred direction, almost as if the universe has a hidden north and south pole. The odds of this happening by chance, less than 1 in 1,000. Some researchers dismiss it as a measurement glitch or an artifact of our solar system's motion, but others suspect something deeper. Dark energy's influence might not be uniform. Imagine blowing up a balloon unevenly. One side stretches faster than the other, leaving wrinkles in unexpected places. If dark energy's push varies across space, it could have imprinted this asymmetry onto the cosmos's earliest light. The implications are staggering. A lopsided universe challenges cosmology's sacred principle, isotropy, the idea that the cosmos looks the same in all directions. If the axis of evil is real, it could mean dark energy isn't just a passive backdrop but an active sculptor, warping spacetime in ways we've yet to map. Some theories propose that dark energy interacts with dark matter differently in certain regions, creating cosmic textures that bend light and twist the CMB's patterns. Others wonder if we're seeing echoes of a pre-Big Bang phase, where exotic physics left scars on the universe's fabric. The Planck satellite's ultra-precise CMB maps only deepened the intrigue. While they smoothed out some earlier anomalies, the axis of evil stubbornly persisted, its signal too strong to ignore. Now, next-generation experiments like the Simons Observatory and CMB-S4 are training even sharper eyes on these patterns, hunting for subtle distortions that could link the axis to dark energy's fingerprints. If they find a connection, it would rewrite our understanding of cosmic evolution, not as a uniform expansion, but as a dynamic, uneven dance guided by unseen forces. Critics argue the anomaly might vanish with better data, a trick of noise or galactic interference, but the longer it lingers, the harder it is to ignore. Perhaps dark energy isn't the serene constant we assumed, but a capricious force with a preference for direction. Or maybe the universe itself is fundamentally unbalanced, its asymmetry woven into the laws of physics from the very beginning. Whatever the answer, the axis of evil reminds us, the cosmos has a flair for drama, and dark energy might be its most enigmatic director. What if dark energy isn't something inside the universe, but a shadow cast by the universe's very edges? That's the spine-tingling premise of holographic dark energy, a theory that takes inspiration from one of physics' most radical ideas, the holographic principle. Picture this: every bit of information in our three-dimensional cosmos might actually be encoded on a two-dimensional surface far beyond what we can see, like a cosmic projector screen. And just as a black hole's interior can be described by data on its event horizon, dark energy could emerge from the universe's hidden boundary, a ripple in reality's deepest code. This isn't just poetic metaphor, it's math with startling consequences. The holographic principle, born from black hole thermodynamics, suggests that the maximum information any region of space can hold isn't proportional to its volume, but to its surface area. Apply that to the entire universe, and suddenly, the vacuum energy driving cosmic acceleration might not be a local force at all. Instead, it's a side effect of quantum information packed onto the universe's hypothetical outer shell, vibrating in ways that stretch spacetime from the edges inward. Imagine blowing up a balloon where the paint on its surface dictates how fast it inflates. That's holographic dark energy in a nutshell, a cosmic marionette pulled by strings we can't see. The theory's elegance lies in solving two puzzles at once. First, it sidesteps the infamous vacuum catastrophe, where quantum field theory predicts a dark energy strength 120 orders of magnitude too large. If dark energy isn't a local quantum foam but a holographic echo, its faint value makes sudden sense. It's diluted across the universe's vast boundary. Second, it offers a fresh take on the Hubble tension. A holographic universe might expand at slightly different rates in different eras, not because dark energy changes, but because the screen encoding it evolves over cosmic time. Critics, though, highlight the theory's slippery grasp on reality. For one, the universe doesn't have an obvious boundary. It's likely infinite or at least unbounded. Proponents counter that the holographic surface could be a theoretical construct, like an observer-dependent horizon, but the math gets murky fast. Others note that holographic dark energy struggles to explain why cosmic acceleration kicked in so late, around 5 billion years ago, when a boundary effect should have been present from the start. Yet the idea gains traction where others falter. When physicists tweak holographic models to match supernova and baryon oscillation data, the fit is uncanny, often better than the cosmological constants. Some versions even predict subtle deviations in gravitational lensing patterns that future telescopes like Euclid could test. And if holography is real, it would mean dark energy isn't just a mystery to solve. It's a gateway to understanding reality's true, lower-dimensional nature. What's mesmerizing here is the sheer audacity of the claim. We're used to forces acting within space, not from space's edges. But if holographic dark energy holds up, it would mean the universe's expansion isn't driven by some exotic substance, but by the way information itself is woven into the cosmos's fabric. The next time you gaze at the night sky, consider this. The emptiness between stars might not be empty at all, but a hologram flickering with the universe's deepest secrets. What if dark energy isn't just a cosmic force but a cosmic chameleon, shifting its properties to blend into different environments? That's the wild idea behind chameleon fields, a theory where dark energy isn't uniform but hides in plain sight, especially in dense regions like Earth or even inside laboratory vacuum chambers. Picture this, a particle so shy that it senses its surroundings. Where gravity is strong, like near a planet, it dampens its effects, staying virtually invisible. But in the vast emptiness of space, where matter is sparse, it unleashes its full repulsive power, driving galaxies apart. It's as if dark energy has been playing hide and seek with us all along, and only now are we building tools sensitive enough to catch it in the act. The hunt for these elusive particles is happening not just in deep space but on tabletops, in labs where scientists are pushing the limits of precision. Take, for example, the extraordinary experiments using atom interferometry devices so sensitive they can measure forces 1 billion times weaker than a feather's weight. By trapping clouds of ultra-cold atoms in vacuum chambers and watching how they move under imperceptible influences, researchers hope to spot the faintest whispers of chameleon fields. If these particles exist, they'd exert a subtle push or pull on the atoms, a signature that wouldn't match any known force. One such experiment at the University of California, Berkeley, even uses a tiny, oscillating marble to probe for chameleons, its microscopic movements monitored for anomalies that could betray dark energy's presence. But why go to such lengths? Because chameleon fields could solve one of dark energy's biggest puzzles: why it's so weak compared to theoretical predictions. If dark energy screened itself in high-density regions, it would explain why we don't feel its effects locally, despite its overwhelming dominance in the cosmic void. This idea isn't just theoretical, it's testable. If chameleons exist, they'd interact differently depending on the density of their environment. A lab experiment near Earth's surface, where gravity is strong, should see a far weaker signal than one performed in deep space. That's why missions like NASA's Cold Atom Lab on the International Space Station are so crucial. They're taking the hunt beyond Earth's gravitational grip, where chameleons might let their guard down. Critics, of course, remain skeptical. So far, no experiment has definitively detected a chameleon field, and some argue that the theory's flexibility makes it hard to falsify. But supporters counter that absence of evidence isn't evidence of absence. We're just now developing the tools to look, and the stakes couldn't be higher. If chameleons are real, they'd upend our understanding of dark energy as a static force, revealing it instead as a dynamic, shape-shifting entity that adapts to its surroundings. What makes this search so thrilling is how it bridges the cosmic and the microscopic. The same force accelerating galaxies apart might be hiding in the quietest corners of a lab, waiting for a detector sensitive enough to expose it. Whether chameleon fields are confirmed or debunked, their pursuit is a testament to science's boldest instinct to chase shadows until they reveal their secrets. And in that chase, we might just uncover a universe far stranger and far more cunning than we ever imagined. The Dark Energy Survey didn't just observe the cosmos, it took its fingerprint, mapping the sky with a precision that borders on the obsessive. For 6 years, this ambitious project trained its 570-megapixel eye on the southern hemisphere, cataloging 300 million galaxies across 1/8 of the visible universe. The result, a treasure trove of data so rich it's rewriting the rules of cosmic expansion. But here's what makes DES truly groundbreaking. It didn't rely on just one method to hunt dark energy. Instead, it combined 4 independent techniques: weak gravitational lensing, galaxy clustering, supernova distances, and baryon acoustic oscillations into a single, cross-checked masterpiece. Think of it as surveying a crime scene with fingerprints, DNA, security footage, and eyewitness accounts all at once. When every clue points to the same suspect, you know you've got something real. Weak gravitational lensing, DES's crown jewel, reveals dark energy's handiwork in the way it warps spacetime. As light from distant galaxies travels toward us, it bends around massive galaxy clusters, distorting their shapes like a funhouse mirror. By analyzing these subtle twists across millions of galaxies, DES could map the invisible scaffolding of dark matter, and by extension, measure how dark energy has reshaped that scaffolding over billions of years. The findings were startlingly precise. Dark energy's density matches the cosmological constant's predicted value to within 2%. That's like weighing the entire universe on a cosmic scale and getting it right down to the last feather. But buried in that mountain of data were also whispers of something unexpected. When DES compared its lensing results with measurements of baryon acoustic oscillations, those frozen sound waves from the early universe, the numbers didn't align perfectly. The discrepancy was slight, barely a blip in the statistics, but in cosmology, even a 2 sigma tension gets scientists leaning forward in their chairs. Could this hint that dark energy isn't perfectly uniform, or that it interacts with dark matter in ways we haven't accounted for? The most tantalizing anomaly appeared in the survey's galaxy clustering data, where the distribution of matter seemed slightly smoother than standard models predicted. It's as if some unseen hand had ironed out cosmic wrinkles faster than gravity alone could explain. Critics argue these deviations could still be noise, statistical flukes in an otherwise pristine dataset. But supporters point to an intriguing pattern. Similar anomalies have cropped up in other surveys, like Planck's cosmic microwave background maps and the Sloan Digital Sky Survey. When independent experiments start seeing the same ghosts, physicists take notice. Some theorists are already crafting models where dark energy's strength fluctuates across space or time, while others wonder if we're glimpsing the fingerprints of an entirely new particle. What makes DES's legacy so enduring isn't just the answers it provided, but the questions it forced us to ask. By constraining dark energy's properties with unprecedented precision, it narrowed the playing field for exotic theories. Quintessence models that predicted rapid evolution mostly ruled out. Certain flavors of modified gravity pushed to the fringe. Yet in that narrowing, DES also exposed cracks in the foundation, tiny but persistent gaps between prediction and observation. Future surveys like Euclid and the Vera Rubin Observatory will zoom in on these anomalies with even sharper tools. But for now, the Dark Energy Survey stands as a testament to how far we've come and how much stranger the truth might still be. After all, in a universe where 95% of everything is invisible, the most exciting discoveries often start with the faintest flickers in the data. Quantum entanglement, Einstein's infamous spooky action at a distance, might hold the key to one of cosmology's biggest mysteries. Picture two particles separated by billions of light years, instantly influencing each other's states as if space between them didn't exist. This bizarre phenomenon defies classical physics, but what if its reach extends far beyond tiny particles? What if entanglement's invisible threads weave through the cosmos itself, tugging at the fabric of space-time and shaping dark energy's relentless push? The idea isn't as far-fetched as it sounds. In the quantum world, entangled particles share a connection that transcends distance, their fates intertwined no matter how far apart they drift. Now imagine scaling this way up to the cosmic level. Some theorists suggest that the vacuum of space, far from being empty, is a seething network of entangled quantum fields. Every cubic centimeter of nothingness could be buzzing with these ghostly links, and over vast distances, their collective behavior might generate a repulsive force eerily similar to dark energy. It's like discovering that the universe's expansion isn't driven by some mysterious substance, but by the sheer density of quantum handshakes stretching space-time from within. One particularly mind-bending model, called entanglement entropy, treats the universe like a hologram where information about its contents is stored on a distant boundary. In this framework, the degree of entanglement between regions of space could directly influence how fast those regions expand. More entanglement, faster stretching. Less slower. This would mean dark energy isn't a static force but a dynamic byproduct of the cosmos's quantum interconnectedness. Think of it as the universe's version of a rubber sheet, only instead of gravity pulling it taut, entanglement keeps tugging it wider. But how would we test such a radical idea? Enter the black hole paradoxes. Black holes, with their unimaginable gravitational pull, also have entropy, a measure of disorder tied to the information they contain. Theorists like Leonard Susskind have shown that this entropy might arise from entanglement between particles inside and outside the black hole. If entanglement can shape spacetime's behavior near these cosmic monsters, could it do the same on a universal scale? Experiments like the holometer at Fermilab are already hunting for faint quantum jitters in spacetime itself, searching for evidence that entanglement's influence isn't confined to the microscopic. Critics, of course, raise valid concerns. Scaling quantum effects to cosmic proportions isn't straightforward. The mathematics often breaks down, leaving gaps in the theory. And if entanglement drives dark energy, why didn't its effects dominate earlier in the universe's history? Supporters counter that entanglement's influence could grow as the cosmos expands, like a web stretching tighter over time. Others propose that dark energy's late-time emergence might reflect a phase transition in the quantum vacuum, where entanglement patterns shifted dramatically billions of years after the Big Bang. The most tantalizing clue might lie in the cosmic microwave background. If entanglement leaves imprints on spacetime's expansion, those subtle twists could be frozen into the CMB's temperature fluctuations. Future telescopes, like the Simons Observatory, might spot these fingerprints, anomalies in the radiation's polarization or distribution that betray entanglement's cosmic role. What makes this theory so compelling isn't just its audacity, but its potential to unify physics' greatest divides. Quantum mechanics and general relativity have long resisted reconciliation, operating by entirely different rules. But if entanglement bridges the gap linking the behavior of particles to the fate of the universe, it could rewrite the textbook on everything from black holes to dark energy. The universe's greatest mystery might not be a force or a substance, but a network of invisible quantum threads quietly holding reality together while tearing it apart. Picture this: a universe where the grand cosmic web, that intricate network of galaxies spanning billions of light years, slowly unravels thread by thread. Not with a violent snap, but with a quiet, relentless drift, as dark energy's invisible hand pulls each cluster of galaxies further apart until they're lost in an endless, expanding void. This isn't just a distant possibility, it's the inevitable fate awaiting our cosmos if dark energy continues unchecked. And the chilling reality: future civilizations, no matter how advanced, might gaze into the night sky and see nothing but darkness beyond their own isolated galactic island. The cosmic web, as we know it, is a masterpiece of gravity's patient work, woven over billions of years. Galaxy clusters, connected by shimmering filaments of dark matter and gas, form the universe's largest structures, like neurons in a vast celestial brain. But dark energy is the disruptor, stretching these filaments thinner and thinner until they finally snap. Simulations show that in roughly 100 billion years, the space between galaxy clusters will expand so rapidly that light from neighboring clusters won't just be redshifted, it will be physically impossible to see. The universe beyond our local group will fade from view entirely, like a ship vanishing over the horizon of an ever-widening ocean. What makes this scenario so haunting is the isolation it implies. Imagine a civilization born in the far future, nestled in a galaxy like Andromeda or the Milky Way. To them, the universe would appear eerily empty. Their telescopes, no matter how powerful, would detect no other galaxies, no cosmic microwave background, no quasars, no trace of the vibrant cosmos we observe today. All evidence of the Big Bang, of the universe's grand history, would be locked away behind an impenetrable curtain of expanding space. They might never know galaxies beyond their own existed, let alone the forces shaping their fate. But here's the twist: even as dark energy severs the cosmic web, it leaves behind cryptic clues. The very isolation of these future galaxy clusters could become a telltale sign of dark energy's dominance. Astronomers of that distant era might notice their local group stars are aging strangely, their light stretched into infrared oblivion by the universe's relentless expansion. Or perhaps they'll detect subtle anomalies in the motion of nearby galaxies, hinting at an unseen force pushing them apart. In a cruel irony, the more dark energy reshapes the cosmos, the harder it becomes to study, leaving future scientists to piece together the universe's story from fragments alone. The fate of the cosmic web isn't just a lesson in astrophysics, it's a reminder of our extraordinary cosmic timing. We live in a golden age of cosmology, where the universe's history is still visible, its clues still within reach. The galaxies haven't yet drifted beyond the horizon. The cosmic microwave background still whispers secrets from the dawn of time, but this window won't stay open forever. As dark energy tightens its grip, the universe's story will fade, leaving only isolated chapters scattered across an ever-darkening expanse. And that raises one final, humbling thought: how many cosmic mysteries have already slipped beyond our grasp, lost to the void of an accelerating universe? Time moves forward. This seems obvious, like water flowing downhill or heat dispersing into cold. But peel back the layers and the arrow of time becomes one of physics' deepest puzzles. Why does cause always precede effect? Why can't we unscramble an egg or remember the future? The answer might lie not in the small-scale rules of particles, but in the vast, invisible grip of dark energy shaping the cosmos itself. At the heart of this mystery is entropy, the universe's tendency toward disorder. A shattered glass doesn't reassemble. Perfume diffuses through a room but never spontaneously gathers back into the bottle. These everyday examples reflect entropy's rise, a one-way street toward chaos. But here's the twist: entropy's relentless climb is tied to space itself expanding. As the universe grows, it creates more room for disorder to spread, like ink diluting in an ever larger pool. And dark energy, it's the force stretching that pool faster and faster, accelerating entropy's march. Think of it this way: in a static universe, entropy would eventually hit a ceiling, a state called heat death, where energy is evenly distributed and nothing changes. But dark energy throws a wrench into that equilibrium. By relentlessly stretching space-time, it ensures there's always new emptiness to fill, always fresh disorder to explore. It's as if the universe is an infinite deck of cards being shuffled faster and faster, making it statistically impossible to ever return to the ordered starting state. The arrow of time isn't just a local rule, it's written into the cosmos's expansion. The connection gets even stranger when you consider black holes. These cosmic vacuum cleaners devour matter and information, increasing entropy in ways we're still untangling. But dark energy's influence might extend even here. As the universe accelerates, distant black holes will eventually be pushed beyond our cosmic horizon, their entropy contributions forever hidden. This cosmic vanishing act could redefine how we calculate the universe's total disorder, and whether time's arrow might one day falter in a universe stretched too thin. Critics argue that dark energy's role in time's flow is still speculative, a tantalizing hint, not a proven link. Yet the math is compelling. When physicists model universes without dark energy, entropy's rise slows dramatically, like a clock winding down. Add dark energy back in, and time's arrow sharpens, its direction locked in by expansion's relentless push. Future experiments probing the quantum nature of space-time might test this idea, searching for subtle entropic fingerprints in the cosmic microwave background or gravitational waves. What's at stake isn't just why we remember the past but not the future. If dark energy steers entropy, it means the flow of time isn't an abstract concept, it's woven into the universe's accelerating fabric. Every second that passes, every irreversible change, from the aging of stars to the firing of neurons in your brain, might owe its direction to an invisible force we're only beginning to understand. And that raises a haunting question. If dark energy's grip ever loosens, would time itself unravel? The numbers don't just disagree, they scream in protest, defying every attempt to reconcile them. Quantum field theory, the most successful framework in physics, predicts that empty space should be a raging storm of energy, with virtual particles erupting into existence and vanishing in a frenzy. Calculate the total energy of this quantum foam, and you'd expect it to warp spacetime so violently that galaxies would be shredded before they could form. Yet when we measure dark energy's actual strength, it's weaker than the theory predicts by a factor of 10 to the power of 120. That's like expecting an ocean and finding a single drop, a discrepancy so vast it's been dubbed the vacuum catastrophe, the most embarrassing failure in modern physics. At the heart of this puzzle lies a cosmic irony. The same quantum mechanics that flawlessly predicts the behavior of particles in accelerators falls apart when applied to the vacuum itself. According to the math, every cubic centimeter of empty space should contain enough energy to boil the universe instantly. Yet somehow, almost all of it cancels out, leaving behind only the faintest whisper, the dark energy we observe. Physicists call this fine-tuning, and it's as if the universe's dials were set with impossible precision. If dark energy were even slightly stronger, galaxies would never have coalesced. Slightly weaker, and gravity would have crushed everything back into a singularity. The odds of hitting this sweet spot by chance are so infinitesimal. It's like balancing a pencil on its tip during an earthquake and expecting it to stay upright for billions of years. So where does all that missing energy go? One leading idea invokes supersymmetry, a hypothetical symmetry between particles that could make opposing quantum fluctuations cancel each other nearly perfectly. Imagine two dancers mirroring each other's moves so precisely that their combined energy appears to vanish. The problem: supersymmetry requires undiscovered particles, and after decades of searching, colliders like the LHC have found no trace of them. Another radical proposal suggests the energy isn't missing at all, it's hidden in extra dimensions, leaking out of our universe like water through a sieve. String theory offers mathematical pathways for this, but without experimental proof, it remains a beautiful guess. Then there's the anthropic argument, the controversial notion that our universe is just one of countless others, each with random values for dark energy. We happen to live in the rare one where the number allowed life to emerge. It's a philosophical grenade tossed into physics. If every possible universe exists, do we even need a deeper explanation? Critics bristle at this, calling it surrender disguised as science. Yet others counter that dismissing it outright ignores the eerie alignment between dark energy's value and the conditions necessary for our existence. The vacuum catastrophe isn't just a gap in our knowledge, it's a chasm, exposing how little we understand about nothingness itself. Future experiments might narrow the divide, from ultra-precise measurements of quantum fluctuations in labs to space telescopes hunting for echoes of higher dimensions. But for now, the numbers still taunt us, a reminder that the universe's greatest mysteries often lurk in the emptiest places. Wormholes, those fantastical shortcuts through space-time, have long been the stuff of science fiction, bending the universe's rules to connect distant stars or even eras in a single step. But what if these cosmic tunnels aren't just theoretical quirks? What if dark energy, the same force ripping the cosmos apart, could be the glue holding them open? It's a dizzying idea. The very phenomenon accelerating galaxies away from each other might also stabilize the universe's most elusive bridges. The math behind this possibility is as elegant as it is speculative. Wormholes, according to Einstein's equations, are possible, but they'd snap shut instantly without some exotic material to prop them open. Picture a tunnel dug through sand. Without reinforcement, the walls collapse. Traditional physics suggests you'd need negative energy, a bizarre substance that repels gravity itself to keep a wormhole stable, and here's where dark energy enters the stage. Its repulsive nature mimics the effects of negative energy on cosmic scales, stretching space-time outward. Could it do the same for a wormhole's throat? Some theorists, like physicist Pedro González-Díaz, argue yes, that dark energy's pervasive push might counteract the crushing weight of a wormhole's own gravity, acting like cosmic scaffolding to keep the passage navigable. But the plot thickens when you consider wormholes' eerie resemblance to black holes. From the outside, both appear as bottomless pits warping space. The difference: a black hole leads to a point of no return, while a wormhole's other end could spit you out somewhere, or someone else. Dark energy might be the key to telling them apart. Recent simulations suggest that wormholes threaded with dark energy could emit unique gravitational wave echoes, subtle ripples distinguishable from black holes' clean mergers. Future detectors like LISA might catch these whispers, offering the first hints that Einstein's bridges are more than just equations. The implications are staggering. If dark energy stabilizes wormholes, it could mean the universe is far more connected than we thought, not just expanding, but intricately laced with hidden shortcuts. Imagine civilizations harnessing these tunnels to traverse impossible distances, or even manipulating dark energy itself to engineer stable passages. Of course, the obstacles are monumental. Wormholes would require conditions so extreme they'd likely vaporize anything trying to pass through. And dark energy's uniformity, its tendency to spread evenly, might make it too diffuse to focus on a single wormhole structure. Yet the mere possibility reshapes how we see dark energy's role. No longer just a destroyer of cosmic bonds, it could also be a cosmic architect, weaving threads through spacetime's fabric. Whether these tunnels exist or not, the idea forces us to ask, if the universe can stretch, bend, and accelerate, what other wonders might be hiding in the math? The answer could rewrite not just our maps of the cosmos, but our understanding of its deepest symmetries. The idea that dark energy's value is perfectly tuned for our existence sounds less like science and more like a cosmic conspiracy theory, yet it's a possibility some of the world's top physicists take seriously. At its core, the anthropic principle suggests a dizzying inversion of logic. Instead of asking why dark energy has the precise strength it does, we should recognize that if it were even slightly different, we wouldn't be here to wonder about it. Think of it like walking into a room where the thermostat is set exactly to your comfort, not because someone adjusted it for you, but because every other setting would have made the room uninhabitable. Critics dismiss this as a cop-out, a way to avoid explaining dark energy's fine-tuning by invoking sheer luck. After all, the odds of a universe with dark energy's observed value, roughly 1 part in 10 to the power of 120, are so astronomically slim that calling it chance feels like declaring a tornado assembling a Boeing 747 from a junkyard. But supporters counter that the anthropic principle isn't about giving up on explanations, it's about narrowing them. If multiple universes exist, each with randomly assigned physical constants, then statistically, some will inevitably land in the life-permitting sweet spot. We just happen to live in one of those rare, hospitable bubbles. The debate turns even thornier when you consider string theory's landscape, a vast mathematical terrain of possible universes, each with different laws and constants. In this framework, dark energy's value isn't a fundamental law but a roll of the cosmic dice, one that, in most cases, would have produced a sterile, empty cosmos. The fact that we find ourselves in a universe where galaxies could form, stars could ignite, and life could emerge isn't a coincidence, it's a selection effect. You don't win the lottery and then ask why your numbers were special. You recognize that someone had to win, and this time it was you. Yet the anthropic principle's biggest hurdle isn't philosophy, it's testability. How do you prove the existence of universes we can't observe? Some theorists propose looking for bruises in the cosmic microwave background, anomalies left by collisions with other bubble universes in the multiverse. Others suggest that if our universe's constants are maximally optimized for complexity, not just barely survivable, it could hint at a deeper principle beyond randomness. But for now, these ideas linger on the edge of science, tantalizing yet just out of reach. What makes this debate so electrifying is how it forces us to confront the limits of scientific inquiry. Is the anthropic principle a profound insight into the nature of reality, or a clever way to sidestep the hard questions? For every physicist who calls it a bitter pill, another sees it as the only way to make sense of dark energy's eerie precision. One thing's certain, in a universe where the rules seem rigged in our favor, the answer might not lie in the stars but in the unlikeliest of statistical flukes. Dark energy might shape the fate of galaxies billions of light years away, but the hunt for its fingerprints isn't confined to deep space. It's happening right here on Earth, in labs where scientists are pushing the boundaries of precision to almost unimaginable extremes. Imagine trying to detect a force so subtle it's drowned out by the gravitational pull of a speck of dust, yet so pervasive it's accelerating the entire universe. That's the monumental challenge facing experiments like those using atom interferometry, where clouds of ultra-cold atoms are suspended in near-perfect vacuums, behaving less like particles and more like waves, their delicate ripples sensitive to the faintest whispers of physics. At the heart of these experiments lies a simple but revolutionary idea. If dark energy interacts with matter at all, even imperceptibly, its presence might subtly alter how atoms behave under meticulously controlled conditions. Picture a single cesium atom chilled to just a millionth of a degree above absolute zero, hovering in a vacuum chamber so empty it makes the void between galaxies seem crowded. Laser pulses split the atom's quantum wave function, sending it along two separate paths before recombining it, like a diver jumping off a cliff and reuniting with their reflection in the water below. Any unexpected shift in the interference pattern could betray the influence of an unseen force, whether it's dark energy or something even stranger. One of the most ambitious of these projects, the Stanford-based Magi's experiment, takes this concept to cosmic scales literally. By dropping atom clouds down a vertical vacuum tube over 200 meters tall, it amplifies the sensitivity to potential dark energy effects by letting gravity do the work over extended free fall periods. The goal, to spot deviations from Einstein's general relativity so minuscule they'd make a hair's width seem vast. If dark energy tugs on atoms differently than known forces, or if it fluctuates in strength even slightly over short distances, these experiments could catch it in the act. But why go to such lengths when telescopes already study dark energy's cosmic effects? The answer lies in a tantalizing possibility. Dark energy might not be uniform. Some theories suggest it could clump or vary in density on small scales, like an invisible mist swirling around us unnoticed. Earth-based experiments could detect these local fluctuations, offering clues about whether dark energy is a static backdrop or a dynamic field that shifts in response to its environment. It's the difference between mapping a breeze by watching distant trees sway and feeling it brush against your skin. Critics argue that lab searchers might be chasing shadows after all. If dark energy's influence is so weak it hasn't visibly altered the solar system's motions over billions of years, why expect it to show up in a meter-scale experiment? Yet supporters counter that quantum sensors have reached such staggering precision that they can now probe forces a billion times weaker than gravity. The mere act of looking could uncover surprises, from hints of extra dimensions to evidence that dark energy interacts with ordinary matter in ways cosmological observations miss. What makes this terrestrial hunt so electrifying is its potential to bridge the cosmic and the quantum. Dark energy's dominion may span the universe, but its secrets could be hiding in the quietest corners of a vacuum chamber, waiting for a flicker of atoms to betray its presence. Whether these experiments confirm dark energy's shadow or force us to rethink it entirely, one thing's certain: the answers won't just come from gazing at the stars, they'll emerge from the infinitesimal dances of particles right here at home. 5 billion years ago, the universe crossed an invisible threshold, a tipping point where the relentless tug of gravity, which had governed cosmic expansion since the Big Bang, finally lost its grip to dark energy's silent dominance. Picture a vast tug of war between two invisible giants. For nearly 9 billion years, gravity had been slowly pulling the cosmos inward, decelerating its expansion like a ball rolling uphill. Then, without warning, the balance shifted. Space itself began stretching faster, not slower, as if an unseen hand had flipped a switch. Galaxies started drifting apart at ever-increasing speeds, their light stretching into longer, redder wavelengths as the vacuum between them grew. This wasn't just a subtle change, it was a cosmic regime change, the moment dark energy seized control of the universe's fate. But what triggered this dramatic shift? To understand, we need to rewind the clock to an era when the universe was far denser. In its youth, matter, both normal and dark, was packed tightly enough that gravity's pull easily outweighed dark energy's feeble push. As the cosmos expanded, matter diluted, spreading galaxies thinner like ink in water. Around 5 billion years ago, the density of matter dropped below a critical point, leaving dark energy as the dominant force. It's like a crowded room emptying out. When few people remain, even a gentle breeze can send them drifting apart. Dark energy, unlike matter, doesn't dilute as space grows. Its strength per cubic centimeter stays constant. So as the universe expanded, its influence grew relative to gravity's fading grasp. The evidence for this transition is etched into the light of ancient supernova. When astronomers compare the brightness of these stellar explosions across different cosmic epochs, they see a clear pattern. Around 5 billion years ago, the universe's expansion curve flips from decelerating to accelerating. The dark energy surveys maps of galaxy clustering reveal the same story. Clumps of matter that once grew denser under gravity's pull began stretching apart as dark energy's repulsion took hold. Even the cosmic microwave background carries hints of this shift, with subtle imbalances in its temperature fluctuations suggesting dark energy was quietly biding its time before emerging as the universe's prime architect. Yet mysteries linger. Why did this handover happen so late in cosmic history? If dark energy's strength is truly constant, why didn't it dominate sooner? Some theorists propose that dark energy might have interacted with dark matter in the early universe, its effects suppressed until a critical threshold was crossed. Others wonder if dark energy isn't static at all, that it might have awoken from a dormant state like a hibernating bear stirring to life, the most radical idea. That we're seeing evidence of a phase transition in the fabric of spacetime itself, akin to water freezing into ice, where the universe's underlying rules reconfigured to favor expansion. The echoes of this cosmic coup are still unfolding. Today, dark energy's grip tightens with every passing second, accelerating the universe toward an increasingly isolated future. Yet by studying this pivotal epoch, the moment gravity's reign ended, we might uncover clues not just about dark energy's nature, but about the universe's ultimate destiny. Was this transition inevitable, or could the cosmos have taken a different path? The answer lies buried in the light of galaxies halfway across the observable universe, waiting for the next generation of telescopes to reveal it. When black holes collide, they don't just shake the fabric of spacetime, they send ripples through the very foundations of physics. These gravitational waves, first detected by LIGO in 2015, are more than just cosmic echoes. They could be hiding subtle distortions caused by dark energy's invisible hand. Imagine two massive black holes spiraling toward each other, warping space and time as they merge. Normally, their gravitational waves follow precise patterns predicted by Einstein's equations. But if dark energy alters how spacetime behaves on cosmic scales, those waves might carry faint anomalies like a song played slightly off-key, betraying the presence of an unseen conductor. The key lies in how gravitational waves travel across the universe. As these ripples pass through regions where dark energy dominates, their shape and frequency could shift imperceptibly. Think of it like light passing through water. It bends and slows, leaving telltale signs of its journey. Dark energy's repulsive push might stretch spacetime in ways that subtly tweak gravitational waves, especially those from mergers billions of light years away. LIGO and its European counterpart, Virgo, are now sensitive enough to catch these deviations. In a groundbreaking study from 2023, researchers combed through dozens of black hole mergers, hunting for inconsistencies in the wave's ring-down phase. the final moments when the newly formed black hole settles into a stable shape. Any mismatch between theory and observation could hint at dark energy's fingerprints, but the real breakthrough might come from next-generation detectors like LISA, the Laser Interferometer Space Antenna. Unlike ground-based observatories, LISA will float in space, free from Earth seismic noise, allowing it to spot lower-frequency gravitational waves, the kind emitted by supermassive black holes merging in the early universe. These ancient collisions occurred when dark energy's influence was just beginning to emerge, offering a pristine test of how it shapes space-time over cosmic time. If LISA detects waves that look stretched or compressed in unexpected ways, it could reveal whether dark energy's strength has changed over billions of years. Critics caution that the signals would be incredibly faint, buried under layers of astrophysical noise, yet even a single anomalous merger could rewrite the rules. Some theories suggest dark energy might interact with black holes themselves, perhaps slowing their spins or altering their event horizons in ways that gravitational waves could expose. Others propose that merging black holes could momentarily stir the quantum vacuum, amplifying dark energy's effects during the collision's violent climax. What makes this hunt so electrifying is its sheer audacity. We're not just observing dark energy's aftermath, we're probing its direct influence on the most extreme objects in existence. Every black hole merger is a cosmic experiment, testing gravity's limits in ways no lab ever could. And if dark energy leaves even the faintest trace in these ripples, it would mean the universe's greatest mysteries are hiding in plain sight, encoded in the echoes of colliding giants. Black holes aren't eternal, at least, not according to Stephen Hawking's most startling prediction. These cosmic monsters, long thought to be the universe's ultimate endpoints, slowly leak energy in the form of Hawking radiation, a faint glow of particles born from quantum fluctuations at the edge of their event horizons. Over unimaginable timescales far longer than the current age of the universe, even the largest black holes would evaporate, vanishing in a final burst of radiation. But here's the twist: dark energy might rewrite that script entirely. What if the very force accelerating the universe's expansion also ensures black holes never truly die? The key lies in the cosmic horizon, the point beyond which light can no longer reach us due to dark energy's relentless push. As space stretches faster, distant galaxies disappear from view, their light redshifted into oblivion. For a black hole, this creates a bizarre paradox. Hawking radiation relies on a temperature difference between the black hole's cold event horizon and the warmer cosmic background. But if dark energy keeps cooling the universe, eventually the background temperature could drop below the black hole's own Hawking temperature. At that point, the black hole would absorb more energy from its frigid surroundings than it emits, effectively freezing in place. It's like trying to melt an ice cube in a freezer that keeps getting colder. The ice stops shrinking and just lingers. This scenario gets even stranger when you consider supermassive black holes. Smaller black holes radiate faster, vanishing in mere billions of years. But the giants at galactic centers, weighing billions of suns, would take googles of years, a one followed by 100 zeros, to evaporate. By then, dark energy might have already isolated them in cosmic voids, cutting off their access to new matter and leaving them to glow faintly against an ever-darkening backdrop. Some models suggest these frozen remnants could outlast even protons, surviving until the universe is an inconceivably ancient sea of near-absolute nothingness. Yet the wildest possibility isn't just survival, it's transformation. If dark energy's strength evolves over time, it could warp space-time so drastically that black holes become causally disconnected from the rest of the universe long before they fully evaporate. Picture a ship sailing toward a horizon that recedes faster than it can travel. The black hole's radiation would stretch into undetectable wavelengths, leaving behind a ghostly imprint, forever hovering on the edge of existence. The irony is poetic. Dark energy, the force tearing the cosmos apart, might also be the reason its most destructive objects never fade away. In a future where galaxies are distant memories and stars no longer shine, the last flickers of Hawking radiation could be all that remains, a cosmic epitaph written in the language of quantum mechanics and spacetime's relentless expansion. Dark energy isn't just stretching the universe apart. It's been quietly pulling the strings behind cosmic evolution since the beginning, shaping everything from the birth of galaxies to the very ingredients that make life possible. Picture the early universe as a vast, simmering soup of matter and energy, where gravity worked tirelessly to clump particles together into stars and galaxies. But dark energy was always there, lurking in the background, subtly counteracting gravity's pull like an invisible hand gently tugging at the fabric of spacetime. Over billions of years, this cosmic tug-of-war determined not just where galaxies would form, but how they'd move, collide, and even fade into isolation. Take galaxy clusters, the universe's largest structures. These colossal cities of stars and gas shouldn't exist in their current form if dark energy hadn't stepped in at just the right moment. Early in cosmic history, gravity dominated, pulling matter into dense knots that eventually became galaxies. But as dark energy's influence grew, it began to stretch the space between these clusters, slowing the rate of new galaxy formation and leaving the universe with a distinctive large-scale structure, threads of galaxies woven into a vast cosmic web, separated by growing voids of near-nothingness. Without dark energy's push, the universe might have been a far denser, more chaotic place, with galaxies packed so tightly that collisions would have been constant, disrupting the delicate conditions needed for stable solar systems and life. Even the chemistry of the cosmos bears dark energy's fingerprints. The elements essential for life, carbon, oxygen, iron, were forged in the hearts of stars and scattered across the universe by supernova explosions. But the distribution of these elements depended critically on how galaxies interacted and merged over time. In a universe without dark energy, galaxies would have merged more frequently, recycling gas and stars at a furious pace, potentially altering the balance of elements we see today. The fact that Earth has just the right mix of heavy elements to support life might be indirectly tied to dark energy's role in pacing galactic evolution, ensuring that star formation and destruction occurred at a rate that allowed complex chemistry to emerge. Now zoom out even further. Dark energy's influence extends to the fate of life itself, not just on Earth but across the cosmos. As the universe accelerates, galaxies beyond our local group will eventually vanish from view, their light stretched beyond detectability. Future civilizations, if they arise, will inherit a far lonelier cosmos, with no evidence of the broader universe beyond their own galaxy. In this way, dark energy doesn't just shape the past and present, it dictates how much of the universe's story will remain knowable in the distant future. We live in a privileged moment, a golden age where the universe's history is still visible, its clues still within reach, the most profound realization. Dark energy's effects aren't just astronomical, they're existential. By governing the expansion of space, it set the stage for the universe we recognize, from the distribution of galaxies to the chemistry of planets. And as its influence grows, it's quietly rewriting the rules of what's possible, isolating islands of matter in an ever-expanding sea of darkness. The next time you look up at the night sky, remember, the stars you see are only visible because dark energy has shaped the cosmos in ways we're only beginning to understand. At the heart of dark energy's mystery lies a deceptively simple symbol, the letter W. This isn't just another variable in a physicist's equation. It's the universe's secret dial, controlling whether dark energy's push grows stronger, weaker, or stays constant across cosmic time. Think of W as the fingerprint of dark energy's true nature, a single number that could reveal whether we're dealing with Einstein's static cosmological constant, a dynamic force field like quintessence, or something even stranger lurking in the equations. The stakes couldn't be higher. If W equals exactly -1, it confirms the cosmological constant dark energy as an unchanging backdrop of space itself. But if W deviates even slightly, everything changes. A value more negative than -1 might signal phantom energy, dooming the cosmos to a big rip. Less negative and dark energy could fade over time, allowing gravity to reclaim dominance. It's the difference between a universe that expands forever in quiet solitude and one that tears itself apart atom by atom. Measuring W isn't just difficult, it's a cosmic detective story spanning billions of years. Astronomers piece together clues from supernova, baryon acoustic oscillations, and gravitational lensing, each method acting as an independent witness to dark energy's behavior. The most precise measurements to date from projects like the Dark Energy Survey peg W tantalizingly close to -1, but with error bars just wide enough to keep theorists awake at night. That slim uncertainty leaves room for dynamism, for the possibility that dark energy today isn't what it was 7 billion years ago. Future missions like ESA's Euclid telescope aim to shrink those error bars to near zero. By mapping billions of galaxies across 10 billion light-years, Euclid could catch dark energy in the act of changing strength, its observations acting as a time machine comparing ancient and modern expansion rates. The real breakthrough would come if W varies not just across time but across space. Imagine dark energy as a cosmic chameleon, stronger in voids and weaker near galaxies. Such a discovery would shatter the cosmological constant paradigm, forcing a rewrite of Einstein's equations themselves. What makes W so revolutionary isn't just its predictive power, it's how it bridges the quantum and cosmic scales. If dark energy's equation of state connects to vacuum fluctuations or extra dimensions, measuring W precisely might be our first direct glimpse of physics beyond the standard model. Every decimal point matters. The difference between -0.99 and -1.01 could determine whether the universe ends in ice, fire, or something beyond our wildest theories. For cosmologists, nailing down W isn't just science, it's the ultimate cosmic prophecy, written in the language of spacetime's expansion. When the James Webb Space Telescope launched on Christmas Day 2021, it carried more than just the hopes of astronomers. It held the potential to rewrite cosmic history. Unlike its predecessor Hubble, which revolutionized our view of the visible universe, JWST specializes in infrared light, allowing it to peer through cosmic dust and capture the faintest glimmers from the universe's infancy. And now it's turning that unprecedented gaze toward one of cosmology's greatest puzzles: when and how dark energy first began shaping the cosmos. The key lies in time travel, not with a fictional machine, but with light itself. Every photon JWST collects from distant galaxies is a messenger from the past, some traveling over 13 billion years to reach us. By measuring the precise redshifts of these ancient galaxies, how much their light has stretched as space expanded, scientists can reconstruct the universe's expansion rate at different epochs. But here's where JWST changes everything. Hubble could see galaxies dating back to about 500 million years after the Big Bang. JWST, It's already smashed that record, spotting galaxies from just 200 million years post-Big Bang, an era when dark energy's influence should have been negligible. Except the data isn't playing by the rules. Early observations from JWST reveal something startling. These primordial galaxies appear brighter and more evolved than standard models predict. That might not sound like a dark energy clue at first, but if galaxies formed faster than expected, it suggests the early universe expanded differently than we thought. One radical explanation: dark energy wasn't just a latecomer to the cosmic stage. It might have been quietly at work even in the universe's first chapters. Imagine a play where the lead actor was supposed to enter in Act 3, but JWST scripts hint they've been lurking in the wings since the opening scene. The telescope's second weapon in this hunt is gravitational lensing. By studying how massive galaxy clusters bend light from objects behind them, a natural magnifying glass, JWST can map the distribution of both visible and dark matter with staggering precision. These maps aren't just snapshots, they're time-lapse videos of cosmic structure formation. When compared to simulations, any mismatch in how quickly voids grew or filaments stretched could reveal dark energy's fingerprints on spacetime stretching. Already, JWST lensing data has uncovered bizarre, overweight galaxies in the young universe, objects so massive they defy conventional growth timelines. Could dark energy have greased the wheels, helping matter clump faster than gravity alone allowed? Yet JWST's most tantalizing contribution might be what it hasn't found. The telescope's deep field images have revealed far fewer faint, distant galaxies than predicted, a discrepancy some theorists link to dark energy's early influence. If the universe expanded slightly faster in its youth than models assume, those missing galaxies might have been pushed beyond detectability, their light stretched into oblivion. It's like arriving at a party expecting a crowd, only to find half the guests left early. The question is, what made them leave? Dark energy's subtle nudge could be the culprit. Of course, every new discovery brings new questions. Could these anomalies stem from unknown galaxy formation physics rather than dark energy? Are we misinterpreting the data? JWST Full Dark Energy Survey, spanning thousands of hours of observation, aims to settle these debates by cross-referencing galaxy redshifts with baryon acoustic oscillation patterns and supernova distances. It will build the most detailed 3D map of cosmic expansion ever made, a map where dark energy's shadow might finally come into focus. What makes JWST mission so pivotal isn't just its cutting-edge optics, it's the telescope's ability to act as a bridge between eras. For the first time, we can compare the universe's toddler years captured in infrared with its adolescence seen by Hubble and adulthood observed by modern telescopes. If dark energy's strength has changed over this span, JWST will catch it in the act. The answers won't just fill textbooks. They could redefine our place in a cosmos where the rules of expansion are still being written. Imagine the universe not just expanding in silence, but humming with an inaudible melody, a vibration so subtle it warps spacetime itself. These hypothetical, dark energy waves aren't your typical gravitational ripples from colliding black holes. They'd be something far stranger, oscillations in the very fabric of dark energy, sending tremors through the cosmos like a plucked string resonating across dimensions. If they exist, these waves wouldn't just be a new phenomenon, they'd be a direct line to understanding dark energy's true nature, revealing whether it's a static field or a dynamic force with its own rhythms and rules. The idea builds on a radical reimagining of dark energy. Instead of a smooth, unchanging backdrop, some theories propose it could behave like a quantum field capable of rippling, similar to how the electromagnetic field produces light waves. These ripples wouldn't travel through space-time. They'd be space-time itself flexing under dark energy's influence. Picture dropping a pebble into a pond. Only the pond is the universe, and the ripples are distortions in the rate of cosmic expansion itself. Detecting them would require instruments sensitive enough to measure fluctuations in the distance between atoms, changes smaller than a proton's width over miles of space. Enter next-generation gravitational wave detectors like LISA and the Einstein telescope. While current observatories like LIGO listen for the thunderous crashes of black holes, these future machines will tune into lower frequencies, the perfect range to catch the faint whispers of dark energy waves. LISA, a space-based trio of satellites set to launch in the 2030s, will float millions of miles apart, firing lasers to measure microscopic shifts in their separation. A passing dark energy wave could stretch one arm of this triangle while compressing another, leaving a signature unlike any gravitational wave we've seen. But the real game-changer might lie in pulsar timing arrays. These networks of dead stars spinning neutron beams that flash with metronomic precision act as cosmic lighthouses. By monitoring their rhythmic pulses across decades, astronomers can spot delays as minuscule as a millionth of a second, clues that space-time itself has wobbled between the pulsar and Earth. In 2023, researchers analyzing data from the Nanograv collaboration found a faint, universe-wide hum in the timing of dozens of pulsars. While the signal matches predictions for gravitational waves from supermassive black hole binaries, some theorists wonder if a fraction could belong to something even more exotic: dark energy waves imprinting their cadence on the cosmos. The challenge: distinguishing dark energy's fingerprint from the cacophony of other cosmic signals. It's like trying to hear a single violin in a symphony orchestra playing at the volume of a supernova. Advanced algorithms and machine learning are now being trained to sift through the noise, searching for patterns that defy conventional explanations. One telltale sign would be a wave that doesn't weaken with distance, unlike gravitational waves which fade as they spread. Dark energy waves tied to the universe's expansion might maintain their strength across billions of light years, a defiance of physics that would instantly mark them as something unprecedented. Critics argue the math is speculative. No confirmed theory predicts dark energy waves unambiguously, yet their potential discovery would rank among the greatest upheavals in cosmology. If detected, they could reveal whether dark energy interacts with other forces, whether it clusters unevenly across space, or even if it's governed by undiscovered particles. For now, the hunt remains a gamble, but one with stakes as vast as the cosmos itself. After all, if the universe is singing, we've only just begun to learn how to listen. At first glance, the Higgs boson and dark energy seem worlds apart. One a fleeting particle that explains mass in quantum mechanics, the other an invisible force stretching the cosmos. But dig deeper and a startling possibility emerges. These two pillars of modern physics might be whispering secrets to each other across the vast scales of reality. The connection starts with a number that's baffled scientists for decades: the Higgs boson's mass. At 125 gigaelectronvolts, it's far lighter than quantum field theory predicts. Calculations suggest quantum fluctuations should have made the Higgs impossibly heavy, inflating its mass to the Planck scale, a staggering 10 to the power of 19 gigaelectronvolts. Yet somehow, against all odds, it landed on a value just right for atoms, stars, and life to exist. This isn't just luck, it's a fine-tuning problem eerily similar to dark energy's inexplicably tiny strength. Both values are absurdly improbable, yet both seem essential for a habitable universe. Here's where things get speculative and thrilling. Some theorists propose these two puzzles share a common solution. If the Higgs field, the invisible ocean of energy that gives particles mass, interacts with whatever drives dark energy, their values might be cosmically linked. Picture a cosmic seesaw. As the Higgs field settles into its low energy state, it could subtly tweak the vacuum energy of space itself, leaving behind just the faint residue we call dark energy. It's like pouring water into a bowl and watching the surface tension adjust to balance the liquid, except the bowl is space-time, and the water is the Higgs field's energy. Experimental clues are sparse but tantalizing. When CERN Large Hadron Collider confirmed the Higgs boson in 2012, it also measured how the Higgs field interacts with other particles. Any deviation from predicted coupling strengths could hint at hidden connections to dark energy. So far, no smoking gun has emerged, but future colliders, like the proposed Future Circular Collider, could probe the Higgs properties with unprecedented precision, searching for anomalies that betray its cosmic role. Critics argue this is wishful thinking. The Higgs and dark energy operate on entirely different scales, with no proven mechanism to bridge them. Yet history shows physics' greatest breakthroughs often come from connecting seemingly unrelated phenomena. Electromagnetism and weak nuclear force were once considered separate, until the electroweak theory united them. Could the Higgs and dark energy be the next great unification? The stakes couldn't be higher. If the Higgs field's value indeed influences dark energy, it would mean the universe's expansion rate isn't arbitrary. It's mathematically tied to the very rules that allow matter to exist. Suddenly, two of physics' greatest fine-tuning problems collapse into one elegant solution. For now, the idea remains a provocative maybe, a thread stretching between the quantum realm and the cosmic horizon, waiting to be pulled. But if it snaps into place, the implications would rewrite not just our understanding of dark energy, but the fundamental architecture of reality itself. Not everyone is convinced dark energy is real. While the majority of cosmologists accept it as the best explanation for the universe's accelerating expansion, a vocal minority argues we might be misreading the cosmic tea leaves entirely. These dissenters propose a radical idea. What if the evidence for dark energy isn't proof of a mysterious force, but a cosmic illusion created by gaps in our observations or flaws in our assumptions? Take the inhomogeneous universe theory. Most cosmological models assume the cosmos is smooth on large scales like a well-mixed batter, with matter evenly distributed when you zoom out far enough. But what if that's not true? Imagine the universe as a lumpy dough with dense clusters of galaxies surrounded by vast, empty voids. If we happen to live in one of those underdense regions, a cosmic bubble, our local measurements could be skewed. Light passing through these voids would experience less gravitational drag, making distant supernova appear dimmer than expected. The result, an illusion of accelerated expansion, when in reality, we're just seeing the effects of an unevenly distributed cosmos. Critics of this idea point to the cosmic microwave background. Planck's precise measurements show a universe that's remarkably uniform on the largest scales, with temperature variations of just 1 part in 100,000. But the dissenters aren't backing down. They argue that even small local irregularities imperceptible in the CMB's broad strokes could still distort our modern expansion measurements. It's like trying to judge the smoothness of a mountain range by looking at a satellite photo. From far enough away, the peaks and valleys blend into an average, but if you're standing in one of those valleys, the ground beneath your feet feels anything but flat. Then there's the calibration controversy. The discovery of dark energy hinges on Type 1, a supernova stellar explosions so consistent they're called standard candles. But what if these candles aren't as uniform as we thought? Recent studies suggest that supernova in younger, metal-rich galaxies might burn slightly brighter than those in older, metal-poor ones. If overlooked, these subtle differences could mimic the signal of cosmic acceleration. Teams like the nearby supernova factory are now reanalyzing decades of data, hunting for biases in brightness measurements that might have tricked us into seeing acceleration where none exists. The boldest skeptics go even further, suggesting Einstein's theory of gravity itself might need tweaking. Modified gravity theories like MUND propose that gravity behaves differently on cosmic scales than in our solar system, strong enough to explain galactic rotations without dark matter, yet subtle enough to mimic dark energy's effects. These models struggle to match all the data, particularly the CMB and baryon acoustic oscillations, but their persistence highlights a crucial truth: science thrives on dissent. Every anomaly, every unexplained discrepancy, is a crack where new physics might slip in. What makes this debate so vital isn't just who's right or wrong, it's how it forces us to question the foundations of cosmology. Dark energy could still be the answer, but the skeptics remind us to keep digging, to test every assumption until the universe's secrets are laid bare. After all, the greatest discoveries often come from those willing to challenge the consensus. Imagine an astronomer from a century ago handed a modern dataset, billions of galaxies mapped across 1/3 of the visible universe, each with precise measurements of distance, brightness, and motion. The sheer volume would be paralyzing. This is the challenge today's cosmologists face, except the data isn't just vast. It's growing exponentially, far outpacing human ability to analyze it. Enter artificial intelligence, the unsung hero in the hunt for dark energy secrets. Machine learning algorithms, trained on simulations mimicking the universe's evolution, are now sifting through petabytes of telescope data, spotting patterns so subtle they'd make even the most seasoned astrophysicist's eyes glaze over. Take the Dark Energy Survey's monumental catalog, 300 million galaxies, each a potential clue to cosmic expansion. Traditional analysis might focus on obvious features like galaxy clusters or supernova. But AI digs deeper. Neural networks inspired by the human brain's structure can detect faint correlations between galaxy shapes, positions, and colors that hint at dark energy's influence. One groundbreaking algorithm, trained on simulated universes with varying dark energy strengths, recently identified a bizarre statistical anomaly. Galaxies in regions of slightly faster expansion tended to align their spins in ways defying random chance. Was this dark energy's fingerprint or just cosmic noise? Without AI, we might never have noticed it at all. The real magic happens when machine learning tackles impossible data. Weak gravitational lensing, where dark matter bends light from distant galaxies, creates distortions often smaller than a pixel in telescope images. Humans can't reliably measure these nanowarps across millions of galaxies, but convolutional neural networks AI specialized in image recognition can. A team at Stanford recently fed an AI system blurry, noise-riddled lensing images, and within hours, it reconstructed dark matter maps with unprecedented precision. The kicker, the AI spotted a curious asymmetry in how voids and filaments distorted light, suggesting dark energy might not push evenly in all directions. If confirmed, this could upend the cosmological constant's century-old assumption of uniformity. But AI's greatest strength might be its ability to surprise us. In 2022, a deep learning model analyzing quasar light curves stumbled onto an unexpected pattern. The farther away quasars were, the more their brightness fluctuations seemed to sync up. After ruling out instrument errors, researchers realized the AI had uncovered a potential link between dark energy and quantum fluctuations in the early universe. The discovery, now dubbed quasar entanglement, remains controversial, but it showcases AI's knack for connecting dots humans wouldn't think to relate. Of course, these silicon detectives aren't flawless. Training AI requires simulated data, and if those simulations are based on flawed physics, the algorithms can inherit those biases. That's why projects like the Camel's Suite run thousands of universe simulations with different dark energy rules, ensuring AI learns to recognize true signals from cosmic mirages. The next frontier, combining AI with quantum computing to model dark energy's quantum roots in real time, a task that would take conventional supercomputers longer than the universe's current age. As telescopes like Vera Rubin and Euclid come online, spewing terabytes of data nightly, AI won't just be helpful, it'll be indispensable. These algorithms are more than tools, they're collaborators, revealing a universe far stranger and more intricate than we ever imagined. And in that partnership, we might just find the key to dark energy's ultimate mystery. What if the universe isn't just expanding but responding? At the furthest edge of cosmology, where quantum physics brushes against philosophy, a radical idea lingers. Dark energy might not be some mindless cosmic force, but a phenomenon subtly entangled with consciousness itself. This isn't science fiction, it's a speculative thread weaving through the work of a handful of physicists who dare to ask whether the observer effect, that strange quantum quirk where measurement alters reality, might scale up to the universe's grandest stage. Picture this: in quantum mechanics, particles exist in fuzzy superpositions until observed, collapsing into definite states only when measured. Now stretch that logic to cosmic proportions. Could the universe's expansion, dark energy's relentless push, be influenced by the presence of observers within it? The math, admittedly speculative, hints at eerie possibilities. Some models suggest conscious observation might interact with the quantum vacuum, the same seething energy soup theorized to fuel dark energy. In this view, every act of perception, from a scientist measuring a galaxy's redshift to a bird registering sunlight, could ripple through spacetime's fabric, tweaking dark energy's dial in ways too subtle to detect. The roots of this idea trace back to physicist John Wheeler's participatory universe hypothesis, where he famously proposed reality emerges from observation. Modern variations take it further. If consciousness isn't just a passive witness but an active participant in shaping quantum states, could its collective weight alter the vacuum energy driving cosmic acceleration? Imagine galaxies as nodes in a vast neural network, their light not just traveling through space but subtly negotiating its expansion with every observation made within them. Critics unsurprisingly pounce on the lack of empirical hooks. Unlike dark energy's measurable effects on supernova or baryon oscillations, consciousness-driven models offer no testable predictions yet. But provocative thought experiments persist. One suggests that if observers do influence dark energy, epochs with more complex life might correlate with slight shifts in expansion rates. Future telescopes, like the Legacy Survey of Space and Time, could scour ancient light for statistical anomalies coinciding with peaks in star formation, and by extension, potential spikes in consciousness. The wildest implication: if consciousness and dark energy are linked, the universe's fate might hinge on more than equations. A cosmos devoid of observers could, in theory, evolve differently than one teeming with life. It's a cosmic twist on the old philosophical question: if a tree falls in an empty universe, does it make a sound or even exist? For now, the idea remains at the fringe, a reminder that the deepest mysteries often lie where science and wonder collide. The next decade is set to rewrite cosmology, not with incremental steps, but with quantum leaps in our understanding of dark energy. At the forefront stands the Vera Rubin Observatory, poised to unleash its legacy survey of space and time in 2025. With a 3.2 gigapixel camera, the largest ever built, it will scan the entire southern sky every few nights, capturing subtle distortions in starlight caused by dark energy's warping of spacetime. But here's what makes it revolutionary. Unlike past surveys limited to snapshots, Rubin will create a time-lapse of the universe, tracking how dark energies grip tightens or weakens over years. Imagine watching a movie of the cosmos instead of studying a single frame. That's the power of this 10-year cinematic voyage into the unknown. Meanwhile, 34 meters above Chile's Atacama Desert, the Extremely Large Telescope, or ELT, will peer deeper into space and further back in time than any ground-based observatory in history. Its primary mirror, spanning half a soccer field, will dissect the light from ancient quasars with unprecedented precision, measuring how dark energy stretched the universe during its tumultuous adolescence. The real game-changer, ELT's ability to spot standard sirens, merging neutron stars whose gravitational waves and light emissions act as cosmic yardsticks. By comparing these sirens' distances across different eras, scientists could catch dark energy red-handed, altering the universe's expansion rate over billions of years. But the most audacious dark energy hunter might be LISA, the Laser Interferometer Space Antenna. Slated for launch in the 2030s, this trio of spacecraft will float millions of miles apart, forming a gravitational wave detector so sensitive it could hear the universe's background hum of colliding black holes from the cosmic dawn. Why does this matter for dark energy? Because these waves encode spacetime's expansion history in their very fabric. If dark energy's strength has fluctuated, LISA pristine recordings untouched by Earth's atmospheric noise might reveal telltale tremors in the waveform, like cracks in a bell's resonance betraying hidden flaws. Then there's the Dark Energy Spectroscopic Instrument, DESI, which has already begun its 5-year mission to map 40 million galaxies and quasars. By tracing baryon acoustic oscillations, those fossilized sound waves from the early universe, DESI isn't just measuring dark energy's current push, it's reconstructing its entire timeline. Early data hints at anomalies in the expansion rate that could force us to rethink whether dark energy is truly constant or a shape-shifting force evolving alongside the cosmos. The wild card, quantum sensors. Labs worldwide are perfecting atomic clocks so precise they could detect dark energy's local fluctuations right here on Earth. Picture this: if dark energy interacts with ordinary matter even faintly, these devices measuring times flow down to attoscons might catch space-time itself pulsating imperceptibly around us. It's a long shot, but the mere possibility electrifies physicists. Dark energy's secrets might hide not in distant galaxies, but in the quiet vibrations of atoms in a vacuum chamber. What ties these missions together is their shared ambition to treat dark energy not as a static puzzle, but as a dynamic story unfolding across time. Each instrument offers a unique lens, some peering into the past, others tracking real-time changes, a few probing for quantum whispers. Together, they form an orchestra of discovery, each playing a distinct note in the symphony of cosmic expansion. And if even one strikes the right chord, the echoes could resonate through physics for centuries. Imagine waking up to a universe where dark energy suddenly flickers out of existence like a cosmic light switch flipped off. The effects wouldn't be subtle. Without dark energy's relentless push, the expansion of space wouldn't just slow, it would slam into reverse as gravity reclaims its throne. Galaxies that were racing apart would now lurch toward each other, drawn together by the cumulative pull of all the matter in the cosmos. The universe's fate would pivot from endless expansion to a crushing collapse, barreling toward a big crunch where everything, stars, planets, even space-time itself, condenses back into a singularity. But the chaos wouldn't start in some distant future. Within months, astronomers would notice something eerie. Distant supernova, once dimmed by the universe's accelerating stretch, now appear brighter than expected. Their light, no longer fighting against dark energy's repulsive grip, would reach us with unexpected intensity. Within decades, the cosmic microwave background, the afterglow of the Big Bang, would show telltale shifts, its temperature fluctuations warping as gravity's dominance reshapes the fabric of space. And within centuries, the night sky would transform. Galaxies in our local group, like Andromeda, would loom larger and brighter as they hurtled toward us, their blue shifted light signaling the universe's inward collapse. The most dramatic changes, though, would unfold on cosmic timescales. Without dark energy, the universe's expansion rate, currently accelerating, would follow the classic coasting trajectory predicted by early 20th century astronomers. But gravity's patience is inexorable. Over billions of years, galaxies would merge in violent collisions, their stars igniting the sky with frenzied bursts of new star formation. The cosmic web, that delicate lattice of filaments and voids, would crumple like a sheet of paper tossed into a fire. Even black holes, the universe's most indestructible objects, would eventually spiral together in cataclysmic mergers, their gravitational waves ringing out as space itself contracts around them. Yet this scenario isn't just a thought experiment, it's a window into how finely tuned our universe truly is. Dark energy's absence wouldn't just alter the future, it would rewrite the past. Without its subtle nudge during the universe's infancy, matter might have clumped too aggressively, forming oversized black holes instead of galaxies. Life-friendly elements like carbon and oxygen, forged in stars, could have been scattered too sparsely to ever coalesce into planets. In other words, a universe without dark energy might not just end differently, it might never have allowed us to exist in the first place. The irony is profound. A force we can't see or directly measure, one that makes up 68% of everything, operates with such precision that tweaking its strength by a fraction would render the cosmos unrecognizable. Whether by cosmic accident or some deeper principle, dark energy's presence isn't just a feature of our universe, it's the linchpin holding its story together. And that raises a haunting question. Are we living in the only possible universe that could have allowed us to ask these questions at all? From Einstein's so-called blunder to the cutting-edge telescopes now scanning the cosmos, the hunt to unravel dark energy has transformed not just our understanding of the universe, but our place within it. What began as a mathematical fudge factor, a humble lambda scribbled into equations to keep the cosmos static, has blossomed into one of science's most profound puzzles. A force so dominant it shapes the fate of galaxies, yet so elusive we've never directly detected it. The irony is almost poetic. The more we learn, the clearer it becomes that dark energy isn't just a mystery to solve, it's a mirror reflecting how much we've yet to discover. Consider how far we've come. A century ago, astronomers debated whether the universe extended beyond the Milky Way. Today, we map billions of galaxies, trace the echoes of the Big Bang, and measure the vacuum energy of empty space with staggering precision. Yet for all our progress, dark energy defies easy explanation. Is it Einstein's cosmological constant, woven into the fabric of space-time, a dynamic field like quintessence, shifting over billions of years? Or something far stranger, a holographic shadow, a quantum entanglement, or even a cosmic response to consciousness itself? the possibilities stretch as vast as the accelerating universe. What's undeniable is how this mystery has reshaped science. Dark energy's discovery didn't just add a new chapter to cosmology, it tore up the old playbook. Gone is the static, predictable cosmos of Newton and even Einstein's early vision. In its place, we have a universe that's alive, evolving, and governed by forces we're only beginning to grasp. Future telescopes like Euclid and the Vera Rubin Observatory will push further, probing dark energy's influence across cosmic time with unprecedented clarity. But the real revolution might come from unexpected places. Lab experiments hunting for chameleon particles, gravitational wave detectors listening for spacetime's whispers, or even AI uncovering patterns in data too subtle for human eyes. The beauty of this quest lies in its unanswered questions. Will we find dark energy's fingerprints in the quantum foam, or discover it's been hiding in black holes all along? Could the Hubble tension crack open entirely new physics, or will the multiverse hypothesis force us to rethink reality itself? Whatever the answer, one thing's certain: the journey will redefine not just cosmology, but our very conception of existence. So which thread of this cosmic tapestry fascinates you most? The phantom stars that might not be black holes, the eerie echoes of Baryon oscillations, or the tantalizing chance that dark energy is rewriting the rules of time itself? Drop your thoughts below and keep looking up. The universe isn't done surprising us yet.